McDonald's fries are the most famous fast food items in the world, but few people know the fascinating process behind making them. Inside massive factories, millions of potatoes are sliced and fried with machine-like precision to create the perfect golden crisp. In this documentary, we take you inside the high-speed production lines that turn simple potatoes into the world's most iconic fries ever. The journey of McDonald's French fries begins long before they reach the restaurant kitchens. It all starts with the careful selection and cultivation of the perfect potatoes. Every fry that ends up in a McDonald's restaurant has been through a rigorous process, ensuring consistency in taste, texture, and appearance. The company relies on specific varieties of potatoes, primarily the Russet Burbank, Russet Ranger, Umatilla Russet, and Shepherdie. These potatoes are chosen for their high starch content, which helps create that signature crispy exterior and fluffy interior when fried. They are also selected for their long, uniform shape, which allows McDonald's fries to be consistently straight and evenly sized. Farmers who grow potatoes for McDonald's work under strict guidelines to meet the company's high standards. The soil must be rich in nutrients, well drained, and have the right pH levels to support optimal potato growth. Before planting even begins, farmers carefully prepare the land. The soil is tilled and aerated to improve its structure, allowing the roots of the potatoes to spread evenly. Proper soil preparation ensures that the potatoes will grow uniformly in size and shape, which is crucial for creating the perfect fries. Once the soil is ready, seed potatoes are selected. These are not actual seeds, but small, specially chosen potato tubers that will sprout and grow into full-sized potato plants. Farmers cut these seed potatoes into pieces, making sure each piece contains at least 1 or 2 eyes, the spots where new growth will emerge. These seed pieces are then treated with an antimicrobial solution to prevent disease and are left to cure for a short period before being planted. When the conditions are right, typically in early spring, the seed potatoes are planted in long, evenly spaced rows using precision planting machines. These machines ensure that each seed piece is placed at a consistent depth and distance from the others. Consistent spacing allows the plants to develop evenly, preventing competition for nutrients and ensuring that each potato grows to an optimal size. As the potato plants grow, they require constant monitoring and care. Farmers use irrigation systems to provide a controlled amount of water, ensuring that the plants receive enough moisture without becoming waterlogged. Too much water can lead to rot, while too little can cause the potatoes to develop poorly. Advanced irrigation systems, including center pivot sprinklers and drip irrigation, help maintain the perfect balance. Pest control is another crucial factor. Farmers use integrated pest management techniques, which combine natural predators, crop rotation, and selective pesticide application to keep harmful insects at bay. Keeping pests under control prevents damage to the potatoes and reduces the need for excessive chemical treatments. Throughout the growing season, McDonald's suppliers test the potatoes for starch content, sugar levels, and overall quality. These tests help ensure that the potatoes are developing the ideal characteristics for frying. Potatoes with too much sugar will turn dark when fried, while those with too little starch won't develop the crispy texture that McDonald's fries are known for. When the potatoes reach maturity, typically after 90 to 120 days, the leaves and stems of the plants begin to wither and die. This signals that the potatoes underground are ready for harvest. However, before harvesting begins, farmers often use a technique called vine desiccation. This involves cutting or chemically drying the potato vines to toughen the skins of the potatoes and make them more resistant to damage during harvesting. Harvesting is done using specialized potato harvesters. These machines carefully dig into the soil, lifting the potatoes while shaking off excess dirt. The potatoes are then conveyed into large storage bins or directly into trucks for transport. To minimize bruising and damage, the harvesters are designed to handle the potatoes gently, using soft conveyor belts and cushioned drops. Once harvested, the potatoes undergo a crucial curing process. This involves storing them in temperature and humidity-controlled environments for several weeks. The curing process allows minor cuts and bruises to heal and strengthens the skins, improving their storage life. During this time, the potatoes are kept at a carefully maintained temperature, typically between 45 degrees Fahrenheit and 50 degrees Fahrenheit, to prevent sprouting and spoilage. After curing, the potatoes are stored in massive, climate-controlled storage facilities. These storage units can hold millions of pounds of potatoes and are designed to keep them in optimal condition for months. Proper ventilation is key, as too much humidity can cause mold and rot, while overly dry conditions can cause the potatoes to shrivel. Before the potatoes are transported to processing facilities, they undergo another round of quality control. Samples are taken and tested for defects, size consistency, starch content, and sugar levels. Any potatoes that don't meet McDonald's strict standards are either sent for use in other food products or discarded. Only the best potatoes make it through to the next stage of the process. Now that the potatoes have been grown, harvested, cured, and stored, they are ready for transport to the processing facilities, where they will be transformed into the famous McDonald's fries. Specialized trucks equipped with temperature control systems transport the potatoes to ensure that they remain in perfect condition during transit. The logistics of transporting millions of pounds of potatoes require precise planning to ensure a steady supply of raw materials to processing plants. Upon arrival at the processing facility, the potatoes are unloaded and undergo an extensive inspection process. Workers and automated scanning systems check for any potatoes that might have developed defects during storage or transport. Any potatoes that fail the inspection are removed from the production line. The selected potatoes are then sent into the processing area, where the transformation into fries begins. The next step in the process is cleaning. The potatoes are loaded onto conveyor belts and passed through a series of high-pressure washers and rotating scrubbers. These machines use powerful jets of water and mechanical brushes to remove any remaining dirt, debris, and residual pesticides. The goal is to ensure that the potatoes are completely clean before they are peeled and cut. Once cleaned, the potatoes are sent to industrial steam peelers. These machines use high-pressure steam to loosen the potato skins, making them easy to remove. The potatoes are then tumbled in rotating drums, where the loosened skins are gently rubbed away. This method of peeling is highly efficient and helps preserve as much of the potato as possible, minimizing waste. After peeling, the potatoes pass through another round of inspection. Advanced optical sorting machines use cameras and sensors to detect any remaining imperfections. If a potato has a blemish or an area of discoloration, the machine automatically removes it from the production line. This ensures that only high-quality potatoes continue to the next stage. Now that the potatoes are cleaned, peeled, and inspected, they are ready to be cut into the familiar fry shape. Industrial cutting machines use high-speed water knives to slice the potatoes with incredible precision. These machines use pressurized water jets to push the potatoes through razor-sharp blades at speeds of up to 117 miles per hour. The result is perfectly uniform fries, ensuring consistency in size and shape across every McDonald's location. After being cut, the fries are rinsed in cold water to remove excess surface starch. This step is essential because too much starch can cause the fries to clump together and fry unevenly. By rinsing away the surface starch, the fries maintain their individual shape and crispiness after cooking. Once rinsed, the fries move on to the next critical step in the process: blanching. Blanching is a partially cooking method that helps preserve the fries' texture, color, and flavor. The fries are briefly submerged in hot water at a precisely controlled temperature, which removes additional sugars and further improves the final texture. This step also ensures that the fries achieve their signature golden color when cooked. Now that the potatoes have been washed, peeled, cut, and blanched, the next critical step in their transformation into McDonald's French fries is the drying process. This stage is essential because excess moisture can interfere with the frying process, preventing the fries from achieving the crispy texture that customers expect. After blanching, the fries emerge wet with a thin layer of surface moisture. If this moisture isn't removed, it will cause the fries to absorb too much oil during frying, resulting in a greasy, soggy texture instead of the signature crispiness. To prevent this, the fries are conveyed into an industrial drying system. These drying machines use high-powered air blowers to remove excess water from the surface of the fries. As the fries move along a conveyor belt, large fans blow heated air over them, gradually evaporating the remaining moisture. The temperature and speed of the drying process are carefully controlled, as drying too quickly can cause the fries to develop an uneven texture, while drying too slowly can lead to unwanted starch gelatinization. To ensure consistency, infrared sensors monitor the moisture content of the fries in real time. If any fries still contain too much moisture after passing through the first drying phase, they may be sent through an additional round of drying before moving forward. This step ensures that every fry is prepared correctly before it reaches the frying stage. Once the fries have been properly dried, they are ready for the first round of frying, known as par frying. This is a crucial step in the McDonald's fry making process, as it sets up the fries for their final cooking once they reach restaurant kitchens. During par frying, the fries are submerged in a carefully maintained blend of oils, which typically includes a mix of canola, soybean, and hydrogenated soybean oils. The oil blend is formulated to provide the ideal balance of flavor, crispiness, and shelf stability. Maintaining the right frying temperature is critical. The oil is heated to approximately 335 degrees Fahrenheit, ensuring that the exterior of the fry sets properly without overcooking the interior. The fries are only in the oil for about 45 to 60 seconds, just long enough for their exterior to begin forming a crisp, golden shell. At this stage, the inside of the fry remains mostly uncooked. The goal of par frying is not to fully cook the fries, but rather to create a stable, structured outer layer that will crisp up perfectly when they are fried a second time in McDonald's kitchens. As the fries move through the fryer, automated stirring mechanisms ensure that they cook evenly. The machines continuously adjust frying times and temperatures based on real-time data collected by sensors in the oil. These sensors monitor changes in oil quality, ensuring that the fries cook consistently and that the oil remains fresh throughout the production process. To maintain oil quality, the frying system is equipped with an automatic filtration system that continuously removes food particles and debris. This prevents burn particles from affecting the taste and color of the fries, ensuring that each batch is cooked under optimal conditions. Additionally, the used oil is periodically replaced to maintain consistency and prevent the fries from absorbing any off flavors. Once the fries have been par fried, they must be cooled quickly to prepare them for freezing. The rapid cooling process prevents overcooking and locks in their texture and flavor. As they exit the fryer, the fries are conveyed through a cooling tunnel where cold air is blasted onto them. This brings their temperature down rapidly, stopping the cooking process before they move on to the freezing stage. Now the fries are ready for individual quick freezing, a process that ensures they remain fresh and retain their texture during transportation and storage. Unlike traditional freezing methods, which can cause ice crystals to form and damage the structure of the fries, IQF rapidly freezes each fry in just seconds, preventing clumping and preserving the ideal texture. As the fries move through the freezing tunnel, they are kept in constant motion to prevent them from sticking together. This ensures that when they are later packaged, they remain separate and can be easily portioned at McDonald's restaurants. The IQF process is one of the most important steps in the production of McDonald's fries, as it allows the fries to maintain their signature quality even after being stored and transported over long distances. Without this rapid freezing process, the texture and flavor of the fries would degrade before they ever reach the restaurants. Now that the fries are frozen, they are ready for packaging. The frozen fries are conveyed to the packaging area, where they are portioned into pre-measured bags. The packaging process is highly automated, ensuring precision and consistency. As the fries enter the packaging machines, they pass through electronic weighing systems that measure out the correct amount for each bag. The machines are programmed to fill bags of different sizes, depending on whether they are destined for restaurants or retail sales. Once the correct amount of fries has been portioned, the packaging machine seals the bags using airtight, food-safe plastic. The sealing process is crucial as it prevents moisture and air from reaching the fries, which could cause freezer burn or spoilage. Each bag is then labeled with information such as batch numbers, expiration dates, and storage instructions. These labels ensure that the fries can be tracked throughout the supply chain and that restaurant staff know how to handle them properly. With the fries now packaged, they are moved to storage freezers, where they remain at sub-zero temperatures until they are ready to be shipped to McDonald's locations worldwide. These massive freezers are designed to keep the fries at a stable temperature, preventing fluctuations that could affect their quality. To maintain efficiency, McDonald's employs a sophisticated inventory management system that tracks the movement of frozen fries from production facilities to distribution centers and, ultimately, to individual restaurants. This system ensures that restaurants always receive fresh shipments and that the fries are used in a first-in, first-out manner to prevent older stock from lingering in storage. Now that the McDonald's fries have been frozen and packaged, the next critical step is their transportation and storage. Ensuring that the fries maintain their quality from the factory to McDonald's restaurants worldwide requires a highly coordinated logistics system. Every detail, from temperature control to packaging integrity, must be carefully managed to prevent any compromise in taste, texture, or safety. Once the fries are sealed in airtight bags and labeled, they are transferred into large freezer storage facilities within the processing plant. These storage freezers maintain a consistent temperature of around -18 degrees Celsius or lower, preventing ice crystal formation, which can degrade the fries' texture. The storage rooms are equipped with high-efficiency cooling systems that circulate air evenly, ensuring that no section of the storage area fluctuates in temperature. Inside these freezers, the fries are stacked onto pallets, which hold multiple cases of packaged fries. Each pallet is organized based on batch numbers and production dates, ensuring that inventory follows a first-in, first-out rotation. This method ensures that the oldest batches are always shipped out first, preventing any fries from sitting in storage for too long. Once ready for distribution, the pallets of frozen fries are loaded onto refrigerated trucks. These trucks, known as reefers, are specially designed to transport perishable goods over long distances without breaking the cold chain. Before loading, drivers and logistics personnel conduct a thorough inspection of the truck's refrigeration system to ensure that it maintains the required sub-zero temperatures throughout the journey. As the fries are transferred from the freezer storage to the trucks, time is of the essence. The fries must remain frozen at all times, so the loading process is highly efficient. Warehouse workers use forklifts to move entire pallets of fries onto the trucks in a carefully coordinated sequence. The doors of the truck are kept closed for as long as possible to prevent warm air from entering. And once loading is complete, the truck's refrigeration system is double-checked before departure. Throughout the transportation process, temperature sensors continuously monitor conditions inside the truck. These sensors send real-time data to logistics teams, who can track the temperature remotely and intervene if any issues arise. If the temperature rises even slightly above the acceptable range, Alarms notify the driver and logistics managers so that corrective actions can be taken immediately. McDonald's fries travel through an intricate global supply chain, often covering thousands of miles before reaching their final destination. Some shipments are sent directly to regional distribution centers, while others may be shipped overseas using refrigerated cargo containers. In the case of international shipments, frozen fries are loaded into specialized shipping containers equipped with advanced cooling units. These containers ensure that the fries remain at the proper temperature, even during extended voyages across oceans. Once the fries arrive at a McDonald's distribution center, they are unloaded and immediately placed into cold storage warehouses. These facilities operate similarly to the freezer storage in processing plants, maintaining sub-zero temperatures and using the FIFO inventory system. The fries remain in these distribution centers until they are scheduled for delivery to specific McDonald's restaurants. At this stage, delivery trucks equipped with refrigeration units transport the fries from the distribution centers to individual McDonald's locations. These trucks are designed for short-haul deliveries, ensuring that the fries remain frozen while en route to the restaurants. The loading and unloading process is again handled with precision, minimizing exposure to warm air to maintain the fries' frozen state. When the fries arrive at a McDonald's restaurant, they are immediately placed into a walk-in freezer. These freezers, located in the back of the kitchen, are maintained at a constant temperature of -18 degrees Celsius or lower. McDonald's staff follow strict protocols when handling frozen fries, ensuring that the cold chain remains intact. To manage inventory efficiently, McDonald's employees use a stock rotation system that ensures older batches are used first. Staff are trained to check expiration dates and packaging integrity before moving fries from the freezer to the cooking area. If any package shows signs of damage or thawing, it is discarded to maintain quality and safety standards. With the fries safely stored in McDonald's freezers, the next stage of the process begins: preparation and cooking. When an order for fries is placed, restaurant staff retrieve a bag of frozen fries from the freezer and transfer it to the fry station. The fry station is equipped with multiple deep fryers, each filled with a specially formulated blend of oils that have been carefully designed to give McDonald's fries their signature taste and texture. Before frying, the fries are measured out using a portioning system that ensures consistency across all orders. This portioning system dispenses the correct amount of fries into a stainless steel fry basket, preventing over or under portioning. Consistency is a crucial factor in McDonald's operations, ensuring that every customer receives the same high-quality product, whether they are ordering fries in New York, Tokyo, or London. Once portioned, the fries are submerged into the hot oil, which is maintained at a precise temperature of around 345 degrees Fahrenheit. The restaurant fryers are equipped with built-in temperature sensors that continuously monitor the oil and make automatic adjustments to keep it at the optimal frying temperature. If the oil becomes too hot, the fries can burn and develop an unpleasant taste. If the oil is too cool, the fries will absorb too much oil, becoming greasy and soggy. The frying process typically lasts for approximately 3 minutes, during which time the fries undergo a dramatic transformation. The high temperature causes the moisture inside the fries to rapidly turn into steam, creating the crispy outer layer that defines McDonald's fries. Meanwhile, the starches inside the fry undergo gelatinization, giving the interior its signature fluffy texture. To ensure even frying, McDonald's fryers use automated timers and shaking mechanisms that periodically agitate the fry baskets. This prevents the fries from clumping together and ensures that every fry is cooked to perfection. Once the fries have finished frying, the baskets automatically rise out of the oil, allowing excess oil to drain. At this point, the fries are still extremely hot and must be handled with care. They are immediately transferred to a stainless steel holding tray, where they are given their final touch: seasoning, McDonald's fries are seasoned with a precise amount of salt, which is evenly distributed using a specialized shaker. The amount of salt added is carefully calibrated to ensure that every fry has the same level of seasoning. Too much salt can overwhelm the delicate flavor, while too little can leave the fries tasting bland. The fries are then transferred to their final serving containers, whether that be a small, medium, or large fry box. McDonald's packaging is designed to retain heat while allowing some airflow to prevent the fries from becoming soggy. The packaging process is also highly standardized, ensuring that every order looks and feels the same. Ensuring that every McDonald's fry meets the company's exacting standards requires an extensive quality control process at every stage of production. From farm to fryer, each step is carefully monitored and tested to maintain consistency in taste, texture, and appearance. These rigorous quality control measures are essential in producing fries that are identical in every McDonald's restaurant worldwide. It all begins at the potato farms, where McDonald's agronomists work closely with farmers to oversee crop development. Soil conditions, irrigation levels, and growing techniques are constantly evaluated to ensure that the potatoes develop the right starch content and texture for frying. Once harvested, samples from each batch are tested for size, shape, sugar content, and moisture levels. Only potatoes that meet McDonald's specifications are approved for processing. At the processing facility, automated optical sorters inspect the potatoes before they enter production. These machines use advanced imaging technology to detect any imperfections such as bruising, rot, or irregular shapes. Any potato that does not meet quality standards is removed from the line. As the potatoes move through peeling, cutting, blanching, and drying, additional checks ensure that each fry maintains the correct dimensions, moisture balance, and uniformity. One of the most critical quality control steps occurs during par frying. Sensors in the fryers constantly measure oil temperature and frying time to ensure that the fries develop the correct texture and color. Samples from each batch are taken and tested for oil absorption, crispness, and interior fluffiness. If any deviations are detected, adjustments are made to the frying parameters to maintain consistency. Once the fries are frozen, further inspections take place. Random samples are pulled from production batches and tested in lab conditions to ensure that freezing has not affected their texture or flavor. Fries are fried, tasted, and measured for crispiness, color, and moisture retention. Any irregularities result in adjustments to processing equipment or procedures. During transportation, strict temperature monitoring ensures that the fries remain frozen at all times. Sensors in refrigerated trucks and shipping containers provide real-time temperature data, ensuring that any fluctuations are immediately addressed. If a shipment experiences even minor temperature inconsistencies, it may be rejected to prevent compromised product quality. Upon arrival at McDonald's restaurants, employees perform additional checks before storing the fries in freezers. Staff are trained to inspect packaging for any signs of damage or thawing. When preparing fries for customers, they follow precise cooking procedures, including setting timers, checking oil temperatures, and following strict portioning and seasoning guidelines. To further ensure quality, McDonald's conducts random in-store testing. Quality control specialists visit restaurants to sample fries and evaluate their texture, taste, and temperature. These evaluations help identify any potential issues in the cooking process, ensuring that customers receive the perfect fries every time. Upon arrival at the factory, the cream undergoes comprehensive testing to verify its fat content, microbial levels, and overall purity. This initial assessment ensures that only the highest quality cream enters the production line. Once approved, the cream is stored in large refrigerated tanks, where it is maintained at a precise temperature to preserve its freshness until processing begins. Standardization is the next critical step in butter production. This involves adjusting the fat content of the cream to a consistent level. usually around 40%, which is optimal for churning into butter. Advanced machinery is employed to blend cream with varying fat contents or to add skim milk as needed. This precise adjustment ensures uniformity in the final product. Standardization also allows factories to produce different types of butter, such as light or extra rich varieties, by altering the fat percentage accordingly. The standardized cream is then pasteurized to eliminate any harmful bacteria and to enhance shelf stability. Pasteurization involves heating the cream to a specific temperature for a set duration, followed by rapid cooling to prevent spoilage. After pasteurization, the cream enters the aging phase. This step is crucial for developing the desired texture and flavor profile of the butter. During aging, the cream is stored at a controlled temperature for several hours, allowing natural enzymes and lactic acid bacteria to work on the fat molecules. For cultured butter production, additional bacterial cultures are introduced during this stage to impart a richer, more complex flavor. The aging process can vary depending on the type of butter being produced, with some recipes requiring longer periods to achieve the desired characteristics. Once the cream has been adequately aged, it moves to the churning stage. In industrial settings, large-scale churns are used to efficiently process vast quantities of cream. The churning process separates the butterfat from the buttermilk through continuous agitation. As the cream is churned, the fat globules begin to coalesce, forming small grains of butter. These grains gradually grow larger as the churning continues, eventually forming a cohesive mass of butter. The buttermilk, which is the liquid component remaining after the fat solids have separated, is drained off and often used in other food products, such as baking ingredients or animal feed. Following churning, the butter mass undergoes washing to remove any residual buttermilk and impurities. Cold water is carefully sprayed over the butter while it is continuously agitated to ensure thorough cleaning. This step is vital for improving the texture and extending the shelf life of the butter. After washing, the butter is worked to achieve the desired consistency. If salted butter is being produced, salt is added at this stage to act as a preservative and enhance flavor. The amount of salt varies based on the specific product requirements and regional preferences. The working process involves kneading the butter to distribute the salt evenly and to expel any remaining water. The packaging phase is the next significant step in butter production. At this point, the butter is shaped into blocks, tubs, or sticks, depending on the intended market. Modern factories utilize automated equipment to shape and package the butter efficiently. Each piece is weighed precisely to ensure accurate portioning. Packaging materials are selected for their ability to protect the butter from environmental factors such as light, air, and moisture, which can degrade its quality. Common packaging options include foil-wrapped blocks, plastic tubs, and stick wrappers. The design of the packaging often incorporates branding elements and nutritional information to appeal to consumers. Throughout the entire production process, quality control measures are rigorously enforced to maintain the integrity of the butter. Multiple checks and tests are conducted at various stages to ensure compliance with safety and quality standards. Microbiological testing confirms the absence of harmful bacteria, while physical tests assess the texture and spreadability of the butter. Chemical analysis verifies the fat content and flavor profiles. Sensory evaluation panels may also assess the taste, aroma, and appearance of the butter to ensure it meets consumer expectations. Any batch that fails to meet these criteria is either reprocessed or discarded to uphold product quality. Factories implementing sustainable practices aim to minimize their environmental impact. Waste materials, such as the buttermilk separated during churning, can be further processed to create valuable byproducts like whey protein. Energy usage is optimized through the recovery of waste heat generated during thermal processes, such as pasteurization, which can be reused within the factory. Water used in washing and cleaning operations is treated before discharge to comply with environmental regulations. These efforts contribute to a more sustainable and eco-friendly production process. Technological advancements have significantly enhanced the efficiency and precision of butter production in factories. Computer-controlled systems monitor and adjust parameters such as temperature, speed, and timing during each stage of the process. Robotics and artificial intelligence are increasingly integrated into factory operations to improve accuracy and reduce human error. For example, automated sensors can detect inconsistencies in the cream's fat content during standardization and make real-time adjustments to correct them. These innovations not only streamline the production process, but also allow for greater customization and flexibility in meeting diverse market demands. Consumer trends play a pivotal role in shaping butter production strategies. With growing interest in health-conscious eating, there is an increasing demand for low-fat or plant-based alternatives. Factories respond by developing new recipes and production methods to cater to these emerging preferences. Transparency in sourcing and production practices is becoming increasingly important to consumers, leading factories to adopt traceability systems that provide detailed information about the origin and journey of their products. This builds trust and enhances brand loyalty among customers. The global market for butter is influenced by a variety of factors, including dietary habits, cultural preferences, and economic conditions. Factories must remain adaptable and responsive to these changes to stay competitive. They invest in research and development to innovate and improve their products continuously. Collaboration with suppliers, retailers, and consumers helps factories understand market needs and align their production strategies accordingly. By leveraging technology, adhering to quality standards, and embracing sustainable practices, butter factories aim to deliver superior products that meet and exceed customer expectations. In the context of industrial butter production, the procurement of raw cream is a meticulous process. Cream is sourced from dairy farms that adhere to stringent quality protocols. Upon arrival at the factory, the cream is tested for fat content, microbial levels, and overall purity. Approved cream is stored in refrigerated tanks at a precise temperature to maintain freshness. Standardization adjusts the fat content to approximately 40%, using advanced machinery to blend cream with varying fat contents or add skim milk as necessary. This step ensures uniformity in the final product and enables the production of different butter varieties by altering the fat percentage. Pasteurization follows standardization, involving heating the cream to a specific temperature for a set duration to eliminate harmful bacteria and enhance shelf stability. After pasteurization, the cream enters the aging phase, where it is stored at a controlled temperature for several hours to develop the desired texture and flavor. Cultured butter production introduces additional bacterial cultures during this stage to impart a richer flavor. Churning separates the butterfat from the buttermilk through continuous agitation, forming small grains of butter that grow larger as the process continues. The buttermilk is drained off and often utilized in other food products. Washing removes residual buttermilk and impurities from the butter mass using cold water while it is continuously agitated. Salt is added during the working process if producing salted butter, enhancing flavor and acting as a preservative. Automated equipment shapes and packages the butter into blocks, tubs, or sticks with precise weighing, ensuring accurate portioning. Packaging materials protect the butter from environmental factors, incorporating branding elements and nutritional information to appeal to consumers. Quality control measures are enforced throughout the production process, with multiple checks and tests ensuring compliance with safety and quality standards. Microbiological testing confirms the absence of harmful bacteria. Physical tests assess texture and spreadability, and chemical analysis verifies fat content and flavor profiles. Sensory evaluation panels assess taste, aroma, and appearance to meet consumer expectations. Sustainable practices minimize environmental impact, recycling waste materials, optimizing energy usage, and treating water before discharge. Technological advancements enhance efficiency and precision with computer-controlled systems, monitoring and adjusting parameters during production. Consumer trends shape production strategies, driving innovation in recipes and methods to meet health-conscious demands and build transparency through traceability systems. Collaboration with stakeholders helps factories understand market needs and align production strategies accordingly, delivering superior products that exceed customer expectations. Industrial butter production involves intricate steps and considerations, balancing tradition with innovation. From cream preparation to final packaging, every stage is meticulously controlled to ensure high-quality butter. Advanced technologies, adherence to quality standards, and sustainability initiatives enhance efficiency and reduce environmental impact. Adapting to consumer trends ensures relevance in a competitive market, demonstrating the industry's commitment to responsible and forward-thinking practices. Butter production in factories combines art and science, transforming simple cream into a beloved staple enjoyed worldwide. The journey of butter from cream to table showcases the complexity and sophistication involved in industrial-scale production. Precise control over every stage, rigorous quality assurance, and integration of modern technologies highlight the dedication to delivering a versatile and delicious product. This exploration reveals the detailed processes and considerations that define butter production in a factory setting. Cream acquisition begins with sourcing from dairy farms, adhering to quality protocols. Testing ensures fat content, microbial levels, and purity meet standards. Approved cream is stored in refrigerated tanks at controlled temperatures. Standardization adjusts fat content to 40% using advanced machinery, enabling uniformity and variety production. Pasteurization eliminates bacteria and enhances shelf stability through precise heating and cooling. Aging develops texture and flavor, with cultured butter benefiting from additional bacterial cultures. Churning separates butterfat from buttermilk, forming grains that grow larger during continuous agitation. Buttermilk is drained off for reuse in other food products. Washing removes impurities using cold water while agitating the butter mass. Salt is added during the working process for flavor enhancement and preservation. Automated equipment shapes and packages butter into blocks, tubs, or sticks, with precise weighing ensuring accurate portions. Packaging materials protect against environmental factors, incorporating branding and nutritional information. Quality control enforces safety and quality standards through microbiological testing, physical assessments, and chemical analyses. Sensory evaluations ensure taste, aroma, and appearance meet expectations. Sustainable practices minimize environmental impact by recycling waste, optimizing energy use, and treating water before discharge. Technological advancements enhance efficiency and precision, with computer-controlled systems monitoring production parameters. Consumer trends drive innovation in recipes and methods, promoting health-conscious alternatives and transparency through traceability systems. Collaboration with stakeholders aligns production strategies with market needs, delivering superior products exceeding customer expectations. The creation of mayonnaise in a factory is an intricate process that combines the precision of science with the artistry of culinary expertise. At its essence, mayonnaise is an emulsion, a delicate blend of oil, water, and egg yolks, stabilized by natural emulsifiers such as lecithin. This journey from raw ingredients to jarred condiment involves numerous steps, each meticulously controlled to ensure consistency, flavor, and safety. It all begins with the procurement of high-quality raw materials. Eggs, vegetable oil, vinegar, and various seasonings form the foundation of mayonnaise production. Eggs, particularly their yolks, are crucial because they contain lecithin, a natural emulsifier that binds oil and water together. These eggs must meet stringent standards for freshness and cleanliness before entering the facility. Similarly, the choice of oil is critical. It must be pure and flavorful, as it significantly influences the taste of the final product. Vinegar serves dual purposes. acting as both a preservative and a flavor enhancer. Additional seasonings like salt, sugar, mustard powder, or garlic extract may also be added depending on the desired variety. Once these ingredients arrive at the factory, they undergo rigorous testing to ensure compliance with quality specifications. Microbial contamination, pH levels, and chemical composition are carefully checked. Approved ingredients are then stored in large tanks or silos under controlled conditions to preserve their integrity until needed. Eggs are often pasteurized at this stage to eliminate any potential pathogens, ensuring the safety of the final product. The heart of mayonnaise production lies in the mixing process, where individual components are transformed into a smooth, creamy emulsion. Initially, egg yolks are blended with vinegar and seasonings in a specialized mixer. This mixture acts as the base, providing the foundation for the emulsion. As the blending continues, liquid vegetable oil is slowly introduced into the mix. The key here is gradual addition. Pouring the oil too quickly can destabilize the emulsion, leading to separation. Advanced machinery, equipped with precise flow control mechanisms, ensures that the oil is incorporated at just the right rate, maintaining stability throughout the process. During this phase, the mechanical action of the mixer helps break down the oil into microscopic droplets, dispersing them evenly within the aqueous phase. Lecithin present in the egg yolks plays a pivotal role here, acting as a bridge between the oil and water molecules to prevent them from separating. This step requires careful monitoring of temperature and speed to achieve optimal results. Too much heat can denature the proteins in the egg yolks, compromising the emulsion, while insufficient agitation might leave the mixture lumpy or inconsistent. Once the initial emulsion has been formed, further adjustments may be made to fine-tune the texture and flavor. Additional ingredients, such as stabilizers or thickeners, may be added to enhance the viscosity of the mayonnaise, ensuring it maintains its creamy consistency over time. Some manufacturers also incorporate antioxidants to extend shelf life and preserve freshness. These additions are done using automated systems that measure quantities with remarkable accuracy, guaranteeing uniformity across batches. After the mixing process is complete, the mayonnaise moves to the homogenization stage. Homogenization involves subjecting the mixture to intense pressure through narrow channels, breaking down any remaining large oil droplets into even smaller particles. This step not only improves the stability of the emulsion, but also enhances the smoothness and silkiness of the final product. Modern factories use sophisticated homogenizers capable of processing vast quantities of mayonnaise efficiently while maintaining consistent quality. Next comes the pasteurization phase, a critical step in ensuring the safety of the mayonnaise. Although the eggs have already been pasteurized earlier in the process, the entire mixture is heated to a specific temperature for a set period to eliminate any residual bacteria or microorganisms. Pasteurization also helps stabilize the flavors, allowing them to meld together harmoniously. After heating, the mayonnaise is rapidly cooled to prevent degradation of its texture or nutritional value. With the mayonnaise now fully prepared, it proceeds to the packaging stage. Here, advanced filling machines dispense precise amounts of the product into jars, bottles, or sachets, depending on the intended market. Packaging materials are chosen for their ability to protect the mayonnaise from light, air, and moisture, which could otherwise compromise its quality. For instance, opaque plastic containers or glass jars with tight-fitting lids are commonly used to shield the contents from external factors. Each package is sealed hermetically to ensure freshness until it reaches the consumer. Quality assurance is woven seamlessly into every aspect of mayonnaise production. Throughout the process, samples are regularly taken and analyzed to verify that the product meets all required standards. Microbiological tests confirm the absence of harmful bacteria, while sensory evaluations assess factors such as color, aroma, and taste. Physical properties such as viscosity and spreadability are also measured to ensure the mayonnaise performs well when used in culinary applications. Any deviations from established norms trigger immediate corrective actions, ensuring that only the highest quality mayonnaise leaves the factory. In addition to producing standard mayonnaise, many factories specialize in creating variations tailored to specific tastes and dietary preferences. Reduced fat versions substitute some of the oil with water or other ingredients to lower calorie content without sacrificing flavor. Low sodium options cater to health-conscious consumers, while organic or vegan alternatives appeal to those seeking more sustainable or plant-based choices. These specialty products require unique formulations and production techniques, showcasing the adaptability of modern manufacturing facilities. Sustainability plays a significant role in contemporary mayonnaise production. Factories increasingly focus on minimizing waste, conserving energy, and reducing environmental impact. Waste oils generated during production are recycled into biofuels or other useful byproducts, while water used in cleaning processes is treated before discharge to comply with ecological regulations. Energy-efficient equipment and renewable energy sources further contribute to greener operations. Moreover, sourcing ingredients responsibly, such as using cage-free eggs or sustainably harvested oils, aligns with growing consumer demand for ethically produced goods. Technological advancements continue to revolutionize the mayonnaise industry. Automation streamlines production lines, enabling faster throughput while maintaining exceptional quality. Artificial intelligence and machine learning algorithms optimize processes by predicting equipment maintenance needs, identifying inefficiencies, and suggesting improvements. Robotics handle repetitive tasks with unmatched precision, freeing human workers to focus on higher value activities. These innovations not only boost productivity, but also allow factories to respond swiftly to changing market demands. Consumer trends heavily influence the evolution of mayonnaise production. With increasing awareness about nutrition and wellness, there is a growing interest in healthier alternatives and transparent labeling. Manufacturers address these concerns by developing innovative recipes and providing detailed information about ingredient origins and production methods. Customization capabilities enable factories to produce niche products catering to regional preferences or emerging dietary fads, such as keto-friendly or gluten-free mayonnaises. Global trade dynamics also shape the way mayonnaise is manufactured. Export markets demand adherence to diverse regulatory frameworks, requiring factories to implement flexible systems capable of meeting varying international standards. Collaboration with suppliers, distributors, and retailers ensures alignment with global supply chains, facilitating timely delivery of products worldwide. Continuous investment in research and development keeps factories at the forefront of technological innovation, ensuring their competitiveness in an ever-evolving marketplace. Beyond the technical aspects of production, the cultural significance of mayonnaise cannot be overlooked. In many regions, it is more than just a condiment. It is a symbol of culinary tradition and innovation. From classic sandwiches to elaborate dressings, mayonnaise serves as a versatile ingredient that enhances countless dishes. Its widespread popularity has driven manufacturers to explore new flavors and textures, expanding its appeal beyond traditional boundaries. For example, flavored varieties infused with herbs, spices, or even fruit extracts offer exciting options for adventurous cooks and diners alike. Factories also prioritize food safety above all else, implementing comprehensive protocols to mitigate risks at every stage of production. Hazard analysis and critical control points. Systems identify potential hazards and establish measures to prevent them. Regular audits and certifications ensure compliance with local and international regulations. Employee training programs emphasize hygiene practices and proper handling procedures, reinforcing a culture of safety throughout the organization. Packaging design plays a vital role in the marketing and distribution of mayonnaise. Modern factories invest heavily in developing attractive and functional packaging solutions that appeal to consumers while protecting the product. Innovations in material science have led to the creation of lightweight yet durable containers that reduce shipping costs and environmental impact. Resealable caps and squeezable bottles enhance user convenience, making it easier for customers to enjoy the product without compromising freshness. Supply chain management is another critical component of successful mayonnaise production. Efficient logistics ensure a steady flow of raw materials into the factory and finished goods out to retailers. Strategic partnerships with suppliers help secure reliable sources of high-quality ingredients, while relationships with distributors facilitate rapid delivery to diverse markets. Real-time data analytics enable factories to forecast demand accurately, optimizing inventory levels and reducing waste. Research and development remain central to the growth, and engineers continuously experiment with new formulations, processing techniques, and packaging technologies to improve product quality and sustainability. Emerging trends in biotechnology and fermentation offer promising avenues for enhancing flavor profiles and extending shelf life. Collaborations with academic institutions and research organizations provide valuable insights into cutting-edge developments that can be applied to commercial production. The economic impact of mayonnaise production extends far beyond the factory floor. It supports jobs in agriculture, transportation, retail, and related industries, contributing significantly to local and national economies. By investing in community initiatives and sustainable practices, manufacturers demonstrate their commitment to corporate responsibility and long-term viability. Programs aimed at reducing carbon footprints, conserving water, and promoting biodiversity align with broader societal goals of environmental stewardship. As consumer preferences evolve, so too does the nature of mayonnaise production. Health-conscious individuals seek products with fewer additives and artificial ingredients, driving manufacturers to adopt cleaner label approaches. Clear communication about ingredient sourcing and production methods builds trust and fosters loyalty among discerning customers. Educational campaigns highlighting the benefits of mayonnaise as part of a balanced diet further reinforce its position as a staple in kitchens worldwide. Finally, the future of mayonnaise production promises exciting possibilities. Advances in automation, digitalization, and artificial intelligence will likely transform traditional manufacturing processes, enabling greater efficiency and flexibility. Personalized nutrition platforms may one day allow consumers to customize their own mayonnaise blends based on individual dietary needs and preferences. Meanwhile, ongoing efforts to reduce environmental impact and promote social responsibility will ensure that mayonnaise remains a beloved and sustainable choice for generations to come. Through precise control of every stage, from ingredient preparation to final packaging, factories ensure that each jar of mayonnaise delivers consistent quality and satisfaction. This exploration reveals the depth and complexity behind the seemingly straightforward process of making mayonnaise, highlighting the dedication and expertise required to bring this indispensable condiment to tables everywhere. The production of olive oil in a factory is a meticulous process that combines ancient traditions with modern technology to create one of the world's most revered culinary staples. Olive oil, often referred to as liquid gold, has been cherished for millennia for its rich flavor, health benefits, and versatility in cooking. The journey from olive groves to bottling lines involves several intricate steps, each designed to preserve the natural qualities of the olives while ensuring consistency and quality. It all begins with the cultivation of olives, which are grown primarily in regions with Mediterranean climates such as Spain, Italy, Greece, and parts of North Africa. The choice of olive variety plays a significant role in determining the flavor profile of the final product. Different varieties produce oils with distinct characteristics. Some are fruity and mild, while others are robust and peppery. Harvesting typically occurs between late autumn and early winter when the olives reach their peak ripeness. Timing is crucial because underripe olives yield less oil, while overripe ones can lead to off flavors. Once harvested, the olives are transported to the factory where they undergo rigorous quality checks. These inspections ensure that only healthy, undamaged fruits are used in production. Any leaves, stems, or debris are removed during this stage to prevent contamination. The cleaned olives are then stored temporarily in ventilated containers to maintain freshness until processing begins. The first step in the factory is washing the olives. This process removes dirt, dust, and any remaining impurities from the surface of the fruit. Clean water is sprayed over the olives while they are gently agitated to ensure thorough rinsing. After washing, the olives proceed to the milling stage, where they are crushed into a paste. Traditionally, stone mills were used for this purpose, but modern factories employ stainless steel crushers or hammer mills for greater efficiency. The goal is to break down the cell walls of the olives, releasing the oil trapped inside. Following milling, the olive paste moves to the malaxation phase. Malaxation involves slowly stirring the paste at a controlled temperature to allow small droplets of oil to coalesce into larger ones. This step is critical because it enhances the extraction rate and improves the quality of the oil by promoting better separation of solids and liquids. The duration of malaxation varies depending on factors such as olive variety and desired flavor profile, but it typically lasts between 20 and 40 minutes. After malaxation, the next step is decantation, where the olive paste is separated into its three main components: oil, water, and solid residue known as pomace. In traditional methods, this was achieved using centrifuges or pressing systems. Modern factories predominantly use horizontal decanter centrifuges, which spin the paste at high speeds to separate the heavier solid particles from the lighter liquid phases. The resulting mixture of oil and water is further refined in a second stage centrifuge, which separates the oil completely from any remaining water or fine particles. At this point, the crude olive oil undergoes additional treatments to refine its quality. Filtration is often employed to remove any residual suspended solids, producing a clearer and more stable product. Some manufacturers also implement cold filtration techniques to preserve the natural flavors and aromas of the oil. For extra virgin olive oil, minimal processing is preferred to retain its superior taste and nutritional value. However, lower grade oils may be subjected to chemical refining processes to improve clarity, color, and shelf life. Storage is another critical aspect of olive oil production. Once extracted, the oil is transferred to large stainless steel tanks where it is kept at controlled temperatures to prevent oxidation and degradation. These tanks are equipped with inert gas systems to displace oxygen, further protecting the oil's quality. During storage, the oil continues to settle, allowing any remaining microscopic particles to sink to the bottom of the tank. Periodic sampling and analysis ensure that the oil maintains its desired characteristics throughout this period. Packaging represents the final stage of the production process. Olive oil is bottled in various sizes and formats, ranging from small glass bottles to bulk plastic containers, depending on the target market. Packaging materials are chosen for their ability to shield the oil from light, air, and moisture, which can negatively affect its quality. Dark-colored glass or opaque plastic bottles are commonly used to protect against UV exposure, while tight-fitting caps ensure an airtight seal. Labels provide important information about the oil's origin, grade, and nutritional content, helping consumers make informed purchasing decisions. Quality control is woven into every aspect of olive oil production. Throughout the process, samples are regularly taken and analyzed to verify compliance with strict international standards. Sensory evaluations assess factors such as aroma, taste, and mouthfeel, ensuring the oil meets expectations for its designated grade. Chemical analyses measure parameters like acidity levels, peroxide values, and fatty acid composition to confirm purity and authenticity. Any deviations from established norms trigger immediate corrective actions, guaranteeing that only the highest quality olive oil reaches the market. In addition to producing standard olive oil, many factories specialize in creating premium varieties tailored to specific tastes and dietary preferences. Extra virgin olive oil, considered the finest grade, is produced using mechanical means only, without heat or chemicals, to preserve its natural flavors and antioxidants. Virgin olive oil undergoes slightly more processing, but still retains much of its original character. Refined olive oil, on the other hand, is treated with chemical agents to neutralize defects and achieve uniformity in taste and appearance. Specialty oils infused with herbs, spices, or citrus extracts offer unique flavor profiles that appeal to adventurous cooks and diners alike. Sustainability is increasingly becoming a priority in olive oil production. Factories adopt eco-friendly practices to minimize waste, conserve resources, and reduce environmental impact. Pomace, the solid residue left after extraction, is often recycled into biofuels or animal feed, reducing landfill contributions. Water used in cleaning processes is treated before discharge to comply with ecological regulations. Energy-efficient equipment and renewable energy sources further contribute to greener operations. Moreover, sourcing olives responsibly, such as supporting local farmers who practice sustainable agriculture, aligns with growing consumer demand for ethically produced goods. Technological advancements continue to revolutionize the olive oil industry. Automation streamlines production lines, enabling faster throughput while maintaining exceptional quality. Artificial intelligence and machine learning algorithms optimize processes by predicting equipment maintenance needs, identifying inefficiencies, and suggesting improvements. Robotics handle repetitive tasks with unmatched precision, freeing human workers to focus on higher value activities. These innovations not only boost productivity, but also allow factories to respond swiftly to changing market demands. Consumer trends heavily influence the evolution of olive oil production. With increasing awareness about nutrition and wellness, there is a growing interest in healthier alternatives and transparent labeling. Manufacturers address these concerns by developing innovative formulations and providing detailed information about ingredient origins and production methods. Customization capabilities enable factories to produce niche products catering to regional preferences or emerging dietary fads, such as organic or keto-friendly options. Global trade dynamics also shape the way olive oil is manufactured. Export markets demand adherence to diverse regulatory frameworks, requiring factories to implement flexible systems capable of meeting varying international standards. Collaboration with suppliers, distributors, and retailers ensures alignment with global supply chains, facilitating timely delivery of products worldwide. Continuous investment in research and development keeps factories at the forefront of technological innovation, ensuring their competitiveness in an ever-evolving marketplace. Beyond the technical aspects of production, the cultural significance of olive oil cannot be overlooked. In many regions, it is more than just a cooking ingredient. It is a symbol of heritage and tradition. From drizzling it over fresh bread to using it as the base for elaborate sauces, olive oil serves as a versatile foundation for countless dishes. Its widespread popularity has driven manufacturers to explore new applications and presentations, expanding its appeal beyond traditional boundaries. Factories also prioritize food safety above all else, implementing comprehensive protocols to mitigate risks at every stage of production. Hazard analysis and critical control. Point systems identify potential hazards and establish measures to prevent them. Regular audits and certifications ensure compliance with local and international regulations. Employee training programs emphasize hygiene practices and proper handling procedures, reinforcing a culture of safety throughout the organization. Packaging design plays a vital role in the marketing and distribution of olive oil. Modern factories invest heavily in developing attractive and functional packaging solutions that appeal to consumers while protecting the product. Innovations in material science have led to the creation of lightweight yet durable containers that reduce shipping costs and environmental impact. Resealable caps and pour spouts enhance user convenience, making it easier for customers to enjoy the product without compromising freshness. Supply chain management is another critical component of successful olive oil production. Efficient logistics ensure a steady flow of raw materials into the factory and finished goods out to retailers. Strategic partnerships with suppliers help secure reliable sources of high-quality olives, while relationships with distributors facilitate rapid delivery to diverse markets. Real-time data analytics enable factories to forecast demand accurately, optimizing inventory levels and reducing waste. Research and development remain central to the growth of the olive oil industry. Scientists and engineers continuously experiment with new formulations, processing techniques, and packaging technologies to improve product quality and sustainability. Emerging trends in biotechnology and fermentation offer promising avenues for enhancing flavor profiles and extending shelf life. Collaborations with academic institutions and research organizations provide valuable insights into cutting-edge developments that can be applied to commercial production. The economic impact of olive oil production extends far beyond the factory floor. It supports jobs in agriculture, transportation, retail, and related industries, contributing significantly to local and national economies. By investing in community initiatives and sustainable practices, manufacturers demonstrate their commitment to corporate responsibility and long-term viability. Programs aimed at reducing carbon footprints, conserving water, and promoting biodiversity align with broader societal goals of environmental stewardship. As consumer preferences evolve, so too does the nature of olive oil production. Health-conscious individuals seek products with fewer additives and artificial ingredients, driving manufacturers to adopt cleaner label approaches. Clear communication about ingredient sourcing and production methods builds trust and fosters loyalty among discerning customers. Educational campaigns highlighting the benefits of olive oil as part of a balanced diet further reinforce its position as a staple in kitchens worldwide. Finally, the future of olive oil production promises exciting possibilities. Advances in automation, digitalization, and artificial intelligence will likely transform traditional manufacturing processes, enabling greater efficiency and flexibility. Personalized nutrition platforms may one day allow consumers to customize their own olive oil blends based on individual dietary needs and preferences. Meanwhile, ongoing efforts to reduce environmental impact and promote social responsibility will ensure that olive oil remains a beloved and sustainable choice for generations to come. Through precise control of every stage, from olive cultivation to final packaging, factories ensure that each bottle of olive oil delivers consistent quality and satisfaction. This exploration reveals the depth and complexity behind the seemingly straightforward process of making olive oil, highlighting the dedication and expertise required to bring this indispensable liquid to tables everywhere. The production of whipped cream in a factory is a highly refined process that combines traditional techniques with modern technology to create one of the most beloved and versatile dairy products. Whipped cream, known for its light, airy texture and rich flavor, has become an essential ingredient in desserts, beverages, and culinary creations worldwide. The journey from raw materials to finished product involves several intricate steps, each meticulously controlled to ensure consistency, quality, and safety. It all begins with the procurement of high-quality cream, which serves as the foundation of whipped cream production. Cream is typically sourced from fresh milk, separated through centrifugation or other mechanical processes to concentrate the fat content. For whipped cream, cream with a fat content of around 35% is ideal, as it provides the necessary structure and stability when aerated. The cream must meet stringent quality standards, including checks for purity, fat content, and microbial levels before entering the factory. Once approved, the cream is stored in refrigerated tanks at a precise temperature to preserve its freshness until processing begins. Upon arrival at the factory, the cream undergoes rigorous testing to ensure it meets the required specifications. This includes microbiological testing to confirm the absence of harmful bacteria, chemical analysis to verify fat content, and sensory evaluations to assess flavor and aroma. Approved cream is then standardized to ensure uniformity across batches. Standardization involves adjusting the fat content to the desired level using advanced machinery that blends cream with varying fat contents or adds skim milk as needed. This step is critical for maintaining consistent product quality and enabling customization for different varieties of whipped cream. After standardization, the cream moves to the pasteurization stage. Pasteurization is a crucial step in ensuring the safety and shelf life of the whipped cream. During this process, the cream is heated to a specific temperature for a set duration, followed by rapid cooling. This eliminates any harmful microorganisms while preserving the cream's natural flavors and nutritional properties. Pasteurized cream is then stored at a controlled temperature to maintain its quality until further processing. The next phase in whipped cream production is stabilization. To enhance the cream's ability to hold air and maintain its fluffy texture, stabilizers such as guar gum, carrageenan, or xanthan gum may be added. These ingredients help prevent separation and improve the cream's whipping properties. Emulsifiers like mono and diglycerides may also be incorporated to ensure smooth blending and even distribution of fat globules during aeration. The choice of stabilizers and emulsifiers depends on the desired characteristics of the final product and regulatory requirements in different markets. Once stabilized, the cream proceeds to the whipping stage, where it is transformed into its characteristic light and airy form. In industrial settings, this is achieved using large-scale whipping machines capable of processing vast quantities of cream efficiently. The whipping process involves introducing air into the cream while agitating it at a controlled speed and temperature. As the cream is whipped, the fat globules coalesce, forming a network that traps air bubbles, creating the signature texture of whipped cream. The degree of aeration is carefully monitored to achieve the desired density and volume. During whipping, additional ingredients such as sugar, vanilla extract, or other flavorings may be incorporated to enhance the taste and appeal of the whipped cream. Sugar not only sweetens the product, but also helps stabilize the foam by increasing viscosity and improving bubble formation. Flavorings are carefully selected and measured to ensure they complement the natural richness of the cream without overpowering it. Some manufacturers produce flavored variations, such as chocolate, coffee, or fruit-infused whipped creams, catering to diverse consumer preferences. After whipping, the cream is cooled to stabilize its structure and prevent degradation. Cooling is typically done in a controlled environment to ensure the whipped cream retains its shape and texture. At this stage, the product may undergo further adjustments to fine-tune its consistency and appearance. Advanced machinery is used to measure parameters such as overrun and firmness, ensuring the whipped cream meets the desired specifications. Packaging represents the final stage of whipped cream production. Modern factories utilize automated equipment to dispense precise amounts of the product into various formats, including aerosol cans, plastic tubs, or flexible pouches. Aerosol packaging is particularly popular due to its convenience and ease of use, allowing consumers to spray the whipped cream directly onto their favorite foods. Nitrous oxide is often used as the propellant in aerosol cans, providing both the means of dispensing and contributing to the cream's light texture. Packaging materials are chosen for their ability to protect the whipped cream from light, air, and moisture, which can affect its quality. Labels provide important information about the product's ingredients, nutritional content, and usage instructions, helping consumers make informed choices. Quality control is an integral part of whipped cream production, implemented throughout every stage of the process. Samples are regularly taken and analyzed to verify compliance with strict international standards. Microbiological tests confirm the absence of harmful bacteria, while physical and chemical analyses assess factors such as overrun, firmness, and fat content. Sensory evaluations evaluate the whipped cream's flavor, aroma, and texture to ensure it meets consumer expectations. Any deviations from established norms trigger immediate corrective actions, guaranteeing that only the highest quality whipped cream reaches the market. In addition to producing standard whipped cream, many factories specialize in creating premium varieties tailored to specific tastes and dietary preferences. Low-fat or non-dairy alternatives cater to health-conscious consumers, while organic options appeal to those seeking more sustainable choices. Specialty flavors and textures offer exciting options for adventurous cooks and diners alike. These variations require unique formulations and production techniques, showcasing the adaptability of modern manufacturing facilities. Sustainability plays a significant role in contemporary whipped cream production. Factories increasingly focus on minimizing waste, conserving resources, and reducing environmental impact. Waste cream generated during production is recycled into animal feed or biofuels, while water used in cleaning processes is treated before discharge to comply with ecological regulations. Energy-efficient equipment and renewable energy sources further contribute to greener operations. Moreover, sourcing cream responsibly, such as supporting local farmers who practice sustainable agriculture, aligns with growing consumer demand for ethically produced goods. Technological advancements continue to revolutionize the whipped cream industry. Automation streamlines production lines, enabling faster throughput while maintaining exceptional quality. Artificial intelligence and machine learning algorithms optimize processes by predicting equipment maintenance needs, identifying inefficiencies, and suggesting improvements. Robotics handle repetitive tasks with unmatched precision, freeing human workers to focus on higher value activities. These innovations not only boost productivity, but also allow factories to respond swiftly to changing market demands. Consumer trends heavily influence the evolution of whipped cream production. With increasing awareness about nutrition and wellness, there is a growing interest in healthier alternatives and transparent labeling. Manufacturers address these concerns by developing innovative formulations and providing detailed information about ingredient origins and production methods. Customization capabilities enable factories to produce niche products catering to regional preferences or emerging dietary fads, such as keto-friendly or gluten-free options. Global trade dynamics also shape the way whipped cream is manufactured. Export markets demand adherence to diverse regulatory frameworks, requiring factories to implement flexible systems capable of meeting varying international standards. Collaboration with suppliers, distributors, and retailers ensures alignment with global supply chains, facilitating timely delivery of products worldwide. Continuous investment in research and development keeps factories at the forefront of technological innovation, ensuring their competitiveness in an ever-evolving marketplace. Beyond the technical aspects of production, the cultural significance of whipped cream cannot be overlooked. In many regions, it is more than just a topping. It is a symbol of indulgence and celebration. From birthday cakes to holiday feasts, whipped cream serves as a versatile ingredient that enhances countless dishes. Its widespread popularity has driven manufacturers to explore new applications and presentations, expanding its appeal beyond traditional boundaries. Factories also prioritize food safety above all else, implementing comprehensive protocols to mitigate risks at every stage of production. Hazard analysis and critical control. Point systems identify potential hazards and establish measures to prevent them. Regular audits and certifications ensure compliance with local and international regulations. Employee training programs emphasize hygiene practices and proper handling procedures, reinforcing a culture of safety throughout the organization. Packaging design plays a vital role in the marketing and distribution of whipped cream. Modern factories invest heavily in developing attractive and functional packaging solutions that appeal to consumers while protecting the product. Innovations in material science have led to the creation of lightweight yet durable containers that reduce shipping costs and environmental impact. Resealable caps and ergonomic handles enhance user convenience, making it easier for customers to enjoy the product without compromising freshness. Supply chain management is another critical component of successful whipped cream production. Efficient logistics ensure a steady flow of raw materials into the factory and finished goods out to retailers. Strategic partnerships with suppliers help secure reliable sources of high-quality cream, while relationships with distributors facilitate rapid delivery to diverse markets. Real-time data analytics enable factories to forecast demand accurately, optimizing inventory levels and reducing waste. Research and development remain central to the growth of the whipped cream industry. Scientists and engineers continuously experiment with new formulations, processing techniques, and packaging technologies to improve product quality and sustainability. Emerging trends in biotechnology and fermentation offer promising avenues for enhancing flavor profiles and extending shelf life. Collaborations with academic institutions and research organizations provide valuable insights into cutting-edge developments that can be applied to commercial production. The economic impact of whipped cream production extends far beyond the factory floor. It supports jobs in agriculture, transportation, retail, and related industries, contributing significantly to local and national economies. By investing in community initiatives and sustainable practices, manufacturers demonstrate their commitment to corporate responsibility and long-term viability. Programs aimed at reducing carbon footprints, conserving water, and promoting biodiversity align with broader societal goals of environmental stewardship. As consumer preferences evolve, so too does the nature of whipped cream production. Health-conscious individuals seek products with fewer additives and artificial ingredients, driving manufacturers to adopt cleaner label approaches. Clear communication about ingredient sourcing and production methods builds trust and fosters loyalty among discerning customers. Educational campaigns highlighting the benefits of whipped cream as part of a balanced diet further reinforce its position as a staple in kitchens worldwide. Finally, the future of whipped cream production promises exciting possibilities. Advances in automation, digitalization, and artificial intelligence will likely transform traditional manufacturing processes, enabling greater efficiency and flexibility. Personalized nutrition platforms may one day allow consumers to customize their own whipped cream blends based on individual dietary needs and preferences. Meanwhile, ongoing efforts to reduce environmental impact and promote social responsibility will ensure that whipped cream remains a beloved and sustainable choice for generations to come. Through precise control of every stage, from cream procurement to final packaging, factories ensure that each container of whipped cream delivers consistent quality and satisfaction. This exploration reveals the depth and complexity behind the seemingly straightforward process of making whipped cream, highlighting the dedication and expertise required to bring this indispensable product to tables everywhere. Producing instant coffee in a factory is a complex process that combines food science, advanced engineering, and cutting-edge machinery to transform coffee beans into a soluble, ready-to-use product. From sourcing and roasting coffee beans to freeze-drying or spray-drying the brewed extract, each step in the production process is meticulously planned to ensure consistency, flavor preservation, and efficiency on a massive industrial scale. Let's take an in-depth look at the step-by-step factory process that goes into making instant coffee. The journey begins with sourcing green coffee beans. Factories procure these beans in large quantities from coffee-growing regions such as Brazil, Colombia, Vietnam, and Ethiopia. Since instant coffee requires consistent flavor profiles, manufacturers often blend beans from various regions to create a balanced and standardized flavor. Upon arrival at the factory, the green coffee beans are subjected to rigorous quality control checks. Samples are tested for size, moisture content, and defects to ensure the beans meet the factory's standards for processing. Once approved, the beans are stored in massive silos made of food-grade stainless steel or aluminum to protect them from contamination, pests, and humidity. These silos are equipped with automated systems that precisely dispense beans onto the production line. The first major step in processing the beans is cleaning. Coffee beans, even after being cleaned at their origin, may still contain impurities such as dirt, stones, sticks, or metal fragments. In the factory, the cleaning process involves several stages. Vibrating screens sift the beans to remove large debris, while air classifiers blow away lighter materials like husks or dust. Magnets are used to extract any metallic particles. Some factories also employ optical sorting machines, which use cameras and sensors to identify and remove defective beans or foreign objects. This thorough cleaning ensures that only high-quality beans proceed to the roasting stage. Roasting is a critical step in developing the rich, complex flavors of coffee. Factories use industrial coffee roasters, which can process thousands of pounds of beans per hour. The roasting process is controlled by highly advanced systems that allow operators to customize the roast profile for specific flavor outcomes. For instant coffee, medium to dark roasts are commonly used, as they bring out bold flavors that translate well into the final soluble product. Roasting temperatures typically range between 370 and 540 degrees Fahrenheit, depending on the desired flavor profile. During roasting, the beans undergo the Maillard reaction, a chemical process that creates the characteristic aromas and flavors of coffee. The roasting equipment includes temperature sensors and real-time monitoring systems to ensure uniform roasting across large batches. Once the roasting is complete, the beans are cooled rapidly to stop the roasting process and prevent overcooking. Factories use air cooling systems or water spray cooling, depending on the setup. Cooling is an important step, as improperly cooled beans can lose their flavor or become brittle. After cooling, the beans are sent to grinding machines. The grinding stage reduces the roasted coffee beans into smaller particles, which will be used for the brewing process. Factories use industrial grinders, such as roller mills or hammer mills, capable of producing a consistent grind size. The grind size is crucial because it affects the extraction process that follows. For instant coffee, a relatively coarse grind is typically used to optimize the brewing process in the factory. The ground coffee is then stored in intermediate holding bins, where it is kept fresh until it is ready to be brewed. Brewing is the next major step in instant coffee production, and it is carried out on an industrial scale. Massive brewing systems, similar to oversized percolators, are used to extract the soluble compounds from the ground coffee. These systems consist of large stainless steel extraction tanks or columns, which are designed to hold thousands of gallons of water and coffee grounds. Hot water is circulated through the coffee grounds at precise temperatures and pressures, mimicking the brewing process used at home, but on a much larger scale. Typically, water temperatures range between 190 and 205 degrees Fahrenheit, and the brewing time is carefully controlled to maximize flavor extraction while minimizing bitterness. The brewed coffee concentrate, a liquid containing the extracted soluble compounds, is then filtered to remove the spent coffee grounds. Factories use advanced filtration systems, such as centrifugal separators or fine mesh filters, to ensure that no solid particles remain in the liquid. The spent grounds are often dried and repurposed as fertilizer or biomass fuel, making use of every part of the raw material. At this stage, the coffee concentrate is a highly aromatic liquid, but it is still far from the final product. The challenge is to transform this liquid concentrate into a stable, dry, and soluble form. Factories use one of two main methods for this: spray drying or freeze drying. Spray drying is a fast and cost-effective method that is commonly used to produce instant coffee powder. The coffee concentrate is first preheated to reduce its moisture content. It is then pumped into a tall, spray drying chamber equipped with nozzles that disperse the liquid into fine droplets. At the same time, hot air, typically around 480 degrees Fahrenheit, is blown into the chamber. As the droplets fall through the chamber, the water in the coffee concentrate rapidly evaporates, leaving behind fine coffee powder. Spray drying is efficient and capable of processing large volumes, but the high temperatures can sometimes lead to a slight loss of flavor and aroma. Freeze drying, on the other hand, is a more delicate and sophisticated process that better preserves the natural flavors and aromas of coffee. The coffee concentrate is first frozen at extremely low temperatures, usually around 40 degrees Fahrenheit, to form solid slabs or granules. These frozen coffee pieces are then placed in a vacuum chamber. Inside the chamber, the frozen water in the coffee undergoes sublimation, a process where ice turns directly into vapor without passing through the liquid phase. This method requires precise control of temperature and pressure and takes longer than spray drying, but it produces high-quality granules of instant coffee that dissolve easily in water. After the drying process, the instant coffee is sifted and graded by particle size to ensure uniformity. Any oversized or undersized particles are removed, and the coffee is blended to create a consistent final product. Factories conduct rigorous quality control tests at this stage, including flavor analysis, solubility testing, and moisture content measurement. These tests ensure that the instant coffee meets the desired standards for flavor, aroma, and texture. Packaging is the final step in the production process, and it is designed to protect the coffee from moisture and preserve its freshness. The dried instant coffee is transported to high-speed filling machines, which dispense precise amounts of coffee into jars, tins, or pouches. Factories use nitrogen flushing systems to replace oxygen in the packaging, as oxygen can degrade the coffee over time. The jars are sealed with airtight lids, while pouches are heat-sealed to maintain freshness. After sealing, the packages move to labeling stations, where automated systems apply branding, ingredient lists, and expiration dates. Each package undergoes a final inspection using vision systems to ensure there are no defects in the seals or labels. Once approved, the packages are packed into cartons or cases using robotic packing systems and prepared for shipping. Pallets of instant coffee are stacked and wrapped for stability before being loaded onto trucks or containers for global distribution. Throughout the entire process, factories rely on advanced automation and engineering to ensure efficiency and consistency. Programmable logic controllers and supervisory control and data acquisition systems monitor and control every stage of production, from roasting and brewing to drying and packaging. Real-time data on temperature, pressure, humidity, and other parameters allows operators to make precise adjustments as needed, minimizing waste and ensuring high-quality output. Hygiene and food safety are also paramount in instant coffee production. Production areas are designed with food-grade stainless steel surfaces, seamless flooring, and clean room environments to prevent contamination. Positive air pressure systems are used to keep airborne particles out of critical areas, and employees are required to follow strict hygiene protocols, including wearing protective clothing and adhering to cleaning schedules. Factories are regularly inspected and certified to meet international food safety standards. Inside a tea factory, the transformation of fresh tea leaves into the familiar tea bags, loose leaf tea, or powdered varieties is a carefully orchestrated process. It is a seamless blend of tradition, precision engineering, and science. Every step of the way, from leaf intake to packaging, is designed to preserve the flavor, aroma, and quality that tea enthusiasts have come to expect. While the type of tea being produced, whether black, green, oolong, or white, dictates specific steps in the process, the overall journey is one of meticulous attention to detail, where both manual expertise and advanced machinery play vital roles. The process begins at the tea gardens, where leaves from the Camellia sinensis plant are plucked at peak quality. For most teas, workers handpick only the top 2 leaves and a bud from each branch, as these tender parts of the plant produce the best flavor and aroma. After harvesting, the leaves are transported to the factory as quickly as possible to prevent spoilage or fermentation during transit. Many tea factories are strategically located near plantations to minimize delays and ensure freshness. Upon arrival at the factory, the tea leaves are weighed and inspected for quality. Modern tea factories are equipped with automated intake systems that separate leaves from debris such as twigs or foreign matter. Vibrating conveyor belts or mechanical sieves are commonly used at this stage to remove unwanted materials. For higher grade teas, additional manual inspections may be carried out to ensure only the finest leaves proceed to the next step. The fresh leaves are then carefully spread out in thin layers on large trays or conveyor belts, marking the beginning of the first stage in tea processing. Withering. Withering is a critical step in tea production, as it reduces the moisture content of the fresh tea leaves and prepares them for the subsequent stages of processing. In the factory, withering is typically carried out in withering troughs, long, shallow trays equipped with a system of fans and controlled airflow. Fresh tea leaves are laid out on these trays, and air is circulated over them for several hours to slowly remove moisture. For black tea, withering may last anywhere from 12 to 18 hours, while green tea requires a shorter withering time, as it needs to retain more of its fresh, grassy flavor. Temperature and humidity are carefully controlled using automated climate systems to ensure consistent results. During this stage, the leaves become softer and more pliable, making them ready for rolling. The next stage is rolling, where the tea leaves are twisted and shaped to release their essential oils and initiate oxidation if required, as with black and oolong teas. Factories use large mechanical rolling machines equipped with heavy, grooved plates or rollers. These machines apply pressure to the leaves, breaking down their cell walls and releasing their natural juices. The released juices react with oxygen in the air, beginning the oxidation process that gives black tea its characteristic flavor and color. Rolling machines can be adjusted to produce different shapes and textures depending on the type of tea being made. For example, green teas may be rolled into tight pellets for varieties like gunpowder tea, while black teas are often left in long, wiry shapes. At this point, the production process diverges depending on the type of tea being manufactured. For black tea, oxidation is the next key step. Oxidation, often mistakenly referred to as fermentation, is a chemical process that darkens the tea leaves and develops the rich, robust flavors associated with black tea. In factories, oxidation typically takes place in large, temperature-controlled rooms, where rolled tea leaves are spread out on trays or conveyor belts. These rooms maintain a controlled environment with high humidity and a temperature of around 77 to 86 degrees Fahrenheit. The leaves are periodically monitored to ensure they achieve the desired level of oxidation, which can take anywhere from 30 minutes to several hours, depending on the tea. As the leaves oxidize, they turn from green to a reddish-brown color, releasing the aromatic compounds that define black tea. In contrast, for green tea production, oxidation is intentionally prevented. To preserve the vibrant green color and fresh vegetal flavor of the leaves, factories employ a process called fixation, also known as kill green. This step involves heating the leaves immediately after rolling to deactivate the enzymes that cause oxidation. Factories use either steam or dry heat for this purpose. For Japanese-style green teas, like sencha, the leaves are steamed in specialized machines, while Chinese-style green teas are often pan-fried in large heated woks or rotating drum roasters. Fixation requires precise temperature control, as overheating can burn the leaves and underheating can fail to stop oxidation completely. Once oxidation or fixation is complete, the next step is drying, which reduces the moisture content of the tea to make it shelf stable. Drying is typically carried out in large industrial dryers or ovens equipped with temperature controls and airflow systems. Conveyor belt dryers, in which the leaves are gradually moved through a heated chamber, are common in large-scale tea factories. The temperature during drying ranges from 194 to 248 degrees Fahrenheit, depending on the type of tea and the desired final moisture content, which is usually around 3 to 5%. This step is crucial for locking in the flavor and aroma of the tea while ensuring it will not spoil during storage. After drying, the tea leaves are sorted and graded. In the sorting process, leaves are separated by size, shape, and quality using a combination of vibrating sieves, air separators, and optical sorting machines. Whole leaves, broken leaves, and small particles are separated into different grades, which are used for various tea products. For instance, whole leaves are often reserved for premium loose-leaf teas, while smaller particles are used for tea bags. Some factories also employ advanced laser sorting machines that can detect and remove any remaining foreign objects or off-spec leaves. Blending is another key step in tea production, especially for brands that aim to create consistent flavor profiles. Many teas are blended by mixing leaves from different regions, harvests, or even types of tea. Blending is carried out in large rotating drums or mixing machines, where precise quantities of different teas are combined to achieve the desired flavor. For flavored teas, additional ingredients such as dried fruit pieces, herbs, or essential oils are added during this stage. For example, Earl Grey tea is made by blending black tea leaves with bergamot oil, while chai blends often include spices like cinnamon, cardamom, and cloves. Once the tea has been blended and sorted, it is ready for packaging. Packaging is a highly automated process in modern tea factories. For loose-leaf tea, the leaves are weighed and sealed in airtight bags, tins, or foil-lined pouches to preserve freshness. For tea bags, the leaves are measured and packed into filter paper, which is then cut and sealed into individual tea bags using high-speed machines. Many factories also produce pyramid-shaped tea bags, which allow for larger leaves and better infusion. After filling, the tea bags are placed into cartons or boxes, which are sealed and labeled with branding, lot numbers, and expiration dates. Throughout the entire process, quality control plays a vital role in ensuring the tea meets rigorous standards. Factories employ trained tea tasters who sample the tea at various stages of production to assess its flavor, aroma, and appearance. Advanced laboratory equipment is also used to measure moisture content, microbial activity, and other parameters that affect the quality and safety of the final product. Additionally, factories must comply with food safety regulations and certifications, such as ISO 22000 or HACCP, to ensure their tea is safe for consumption. Cocoa powder, the cornerstone of countless recipes from rich chocolate cakes to creamy hot cocoa, is the product of a complex and fascinating manufacturing process that combines agricultural expertise with advanced industrial engineering. Behind every tin or packet of cocoa powder lies a detailed, multi-step operation where raw cacao beans are transformed into the fine, flavorful powder that has become a staple ingredient in kitchens around the world. This process begins on cacao farms and culminates in a factory where specialized equipment and precise techniques ensure the consistency, flavor, and quality of the finished product. Let's take an in-depth journey into how cocoa powder is made, exploring each stage of the process, from bean to powder. The story of cocoa powder begins with the cacao tree, which thrives in tropical regions near the equator, such as West Africa, Southeast Asia, and Central and South America. The cacao tree produces pods that contain cacao beans surrounded by a sweet, sticky pulp. These beans are the raw material for cocoa powder. Once harvested, the pods are split open to extract the beans, which are then immediately subjected to the first critical step in the process: fermentation. Fermentation is a natural and essential process that develops the flavor precursors in cacao beans. After being removed from the pods, the beans and their surrounding pulp are placed into shallow wooden boxes or large banana leaf-lined baskets, where they ferment over a period of 5 to 7 days. During this time, natural yeasts and bacteria break down the sugars in the pulp, generating heat and causing the temperature in the fermentation pile to rise significantly, often reaching over 120 degrees Fahrenheit. This heat triggers a series of chemical reactions within the beans, developing their characteristic chocolate flavor while reducing bitterness. The beans are turned periodically to ensure even fermentation and prevent spoilage. Once fermentation is complete, the beans are removed from the boxes or baskets and sent to the next stage: drying. Drying is critical for stabilizing the fermented beans and reducing their moisture content to a level suitable for storage and transport. Traditionally, cacao beans are dried under the sun, spread out in thin layers on large drying racks or patios, and turned regularly with wooden rakes to ensure even drying. In modern cocoa production, factories may use mechanical dryers when weather conditions are unsuitable for sun drying or to speed up the process. These machines blow heated air over the beans to achieve the target moisture content, which is usually around 6 to 7%. Proper drying is essential because any excess moisture could lead to mold growth during storage or shipping. Once dried, the beans are sorted, graded, and packed into jute bags or bulk containers, ready for shipment to processing facilities. Upon arriving at the cocoa processing factory, the dried cacao beans are carefully inspected for quality. Factories use advanced optical sorting machines equipped with cameras and lasers to identify and remove defective beans, such as those that are cracked, moldy, or undersized. Any remaining debris, like stones or twigs, is removed using vibrating screens and air separators. Once the beans are cleaned, they are stored in large silos made of food-grade stainless steel, which protects them from contamination while allowing for easy access as the beans move through the production line. The first step inside the factory is roasting, a critical stage that brings out the rich chocolatey aroma and flavor of the beans. Industrial roasters are designed to handle large volumes of cacao beans, roasting them at precise temperatures that can range from 250 to 300 degrees Fahrenheit. The exact temperature and duration of roasting depend on the type of cocoa powder being produced, as darker roasts develop more intense flavors, while lighter roasts preserve subtle fruity or floral notes. During roasting, the shells of the beans become brittle, and the internal nibs, which contain the cocoa solids and cocoa butter, begin to separate from the shell. Sensors and computer-controlled systems monitor the roasting process to ensure consistency across batches. Once roasting is complete, the beans are rapidly cooled, using air or water to prevent overcooking. The next stage is winnowing, where the roasted beans are cracked open to separate the nibs from the outer shells. This process is carried out using winnowing machines, which use a combination of mechanical rollers and air currents to break the shells and blow them away. The result is a pile of clean, roasted nibs, which are the purest form of cacao and the raw material for all cocoa products. The nibs are then ground into a thick, viscous liquid known as cocoa liquor, despite containing no alcohol. The grinding process involves heavy-duty industrial grinders, such as roller mills or stone grinders, which crush the nibs into tiny particles. This process releases the natural cocoa butter within the nibs, creating a smooth liquid that flows easily. The particle size is reduced to less than 30 microns during this stage to ensure a silky texture. Cocoa liquor is the base ingredient for many chocolate products, but for cocoa powder production, the focus shifts to separating the two main components of the liquor, cocoa solids and cocoa butter. The separation of cocoa solids and cocoa butter is achieved through pressing. Cocoa liquor is fed into hydraulic or screw presses, which apply immense pressure, up to 6,000 pounds per square inch, to squeeze out the cocoa butter. This process leaves behind a solid cake of compressed cocoa solids. The extracted cocoa butter is collected and filtered for use in other products, such as chocolate bars, cosmetics, or pharmaceuticals. Meanwhile, the cocoa cake, which still contains a small amount of residual fat, becomes the foundation for cocoa powder. The cocoa cake is cooled and broken into smaller chunks before being fed into pulverizing machines, where it is ground into a fine powder. Factories use various types of grinding equipment, such as pin mills or ball mills, to achieve the desired particle size for cocoa powder. This step is critical for ensuring that the final product has a consistent texture and dissolves easily in liquids. The fineness of cocoa powder can vary depending on its intended use. For example, baking-grade cocoa powder is typically ground finer than drinking cocoa. At this point, the cocoa powder is almost ready, but one additional process may take place depending on the type of cocoa being produced: alkalization. Also known as Dutch processing. Alkalization involves treating the cocoa powder with an alkaline solution, such as potassium carbonate. This process neutralizes the natural acidity of the cocoa, darkens its color, and gives it a smoother, milder flavor. Alkalized cocoa powder is often used in baking and beverages, as its reduced acidity reacts differently with leavening agents like baking soda. Once the cocoa powder is fully processed, it undergoes rigorous quality control tests to ensure it meets the manufacturer's standards. Samples are tested for flavor, color, pH levels, fat content, and particle size. Factories use advanced laboratory equipment, such as spectrophotometers and viscometers, to measure these properties with precision. Any deviations from the desired specifications are identified and corrected before the product moves to the packaging stage. Packaging is the final step in the production process, and it plays a critical role in preserving the freshness and quality of the cocoa powder. The powder is first sifted to remove any clumps or oversized particles, ensuring a uniform texture. It is then transferred to automated filling machines, which dispense precise amounts of cocoa powder into containers, such as tins, pouches, or bulk bags. For retail packaging, the containers are often flushed with nitrogen gas before sealing to remove oxygen and prevent spoilage. Labels are applied to the packages, including information such as the brand, product type, lot number, and expiration date. Once packaged, the cocoa powder undergoes a final round of inspections, where advanced vision systems check for defects such as improper sealing, misaligned labels, or damaged containers. The finished products are then packed into cartons or cases using robotic packaging systems. Palletizing robots stack the cartons neatly onto pallets, which are shrink-wrapped for stability and loaded onto trucks or shipping containers for distribution. Bananas begin their journey in the tropical plantations, where they are carefully cultivated to meet the demands of the global market. The process starts with the selection of optimal banana varieties, with Cavendish bananas being the most widely produced due to their durability and resistance to transportation stress. The banana plants, which are technically large herbs rather than trees, are cultivated in nutrient-rich soil under warm and humid conditions. Farmers carefully monitor the growth of banana plants, ensuring that they receive the right amount of water, nutrients, and protection from pests and diseases. Once the bananas reach the correct stage of maturity, typically around 9 months after planting, the harvesting process begins. Workers use sharp machetes or mechanical cutting tools to carefully cut the large banana bunches, which can weigh up to 50 kilograms. These bunches are placed onto conveyor systems or carried manually to avoid damage. Harvested bananas are quickly transported to centralized collection points, where they undergo a thorough sorting and initial quality inspection. Workers remove any damaged or overly ripe bananas, ensuring only the best quality fruit continues through the production process. The bananas are then washed in large water tanks, often infused with disinfectants to remove dirt, sap, and potential contaminants. This washing step also helps prevent the spread of diseases and fungi that could compromise the fruit's shelf life. Once cleaned, the bananas move onto grading stations, where they are categorized based on size, shape, and external appearance. Factory production standards dictate that only bananas meeting strict criteria proceed to the next stage. At this point, the bananas are separated from the large bunches into smaller clusters, typically consisting of 4 to 7 bananas. These clusters are cut with precision to maintain a uniform presentation. Automated machines or skilled workers carefully trim excess stems to the appropriate length, preventing damage during transportation and further processing. After trimming, the bananas are once again rinsed and placed onto conveyor belts, leading to the next stage of processing. Temperature control is crucial throughout the handling of bananas. To slow down ripening and ensure the fruit remains in peak condition, the bananas are placed in large cooling rooms set to around 13 to 15 degrees Celsius. These controlled conditions help preserve the bananas during transportation to industrial processing facilities, where they undergo further treatment, packaging, and preparation for global distribution. Bananas are highly perishable, so every step of the journey is carefully managed to maximize freshness. Once the bananas arrive at a dedicated processing facility, they undergo another round of inspections. Workers and automated sorting systems check for any defects that may have developed during transportation. The bananas are then placed into climate-controlled storage areas, ensuring that they do not ripen too quickly before packaging. Some bananas are destined for direct sale, while others will be processed into banana-based products such as dried bananas, banana puree, or banana chips. Each of these processing paths requires different equipment and techniques to achieve the desired final product. For fresh banana packaging, the fruit is arranged in trays or cartons designed to protect them from bruising. Packing lines employ automated machinery that gently places the bananas into their designated packaging, ensuring consistent weight and size in each package. Special padded trays or foam inserts are often used to cushion the bananas and minimize damage. The packaged bananas are then labeled, with stickers applied either manually or by automated applicators. These labels often include barcodes, brand names, and country of origin details. To extend shelf life and prevent premature ripening, some banana shipments are treated with ethylene inhibitors. These substances help slow down the natural production of ethylene gas, which is responsible for the ripening process. In cases where bananas need to ripen on demand, specialized ripening chambers are used at distribution centers. These chambers allow controlled exposure to ethylene gas, ensuring the bananas reach optimal ripeness just before being sent to retail stores. For bananas that will be further processed into products like banana chips, the production process involves additional steps such as peeling, slicing, and dehydration. High-speed peeling machines are used to remove the thick banana skins efficiently. The peeled bananas are then transported via conveyor belts to slicing machines, which cut them into uniform pieces based on the desired end product. These slices are then either fried in hot oil to create banana chips or placed in large dehydration ovens to produce dried banana snacks. The production of banana puree involves an entirely different set of machinery and techniques. After peeling, the bananas are mashed using industrial pulping machines, which break down the fruit into a smooth consistency. The puree is then passed through filtration systems to remove any fibrous material or unwanted particles. Depending on the intended use, the banana puree may undergo pasteurization, a heating process designed to kill bacteria and extend shelf life. The final product is then packaged in large containers or smaller, retail-friendly pouches. Throughout every stage of banana processing, quality control measures are strictly enforced. Automated sensors and human inspectors check for consistency in size, shape, color, and taste. Any defective or subpar bananas are removed from the production line and either repurposed for animal feed, compost, or other secondary uses. Ensuring food safety is paramount, and factories adhere to strict sanitation protocols to prevent contamination. Conveyor belts, slicing machines, and packaging stations are regularly cleaned and maintained to uphold hygiene standards. Once the bananas or banana-based products are ready for distribution, they are carefully loaded onto climate-controlled trucks or shipping containers. These vehicles maintain a stable temperature to prevent premature ripening or spoilage. The journey from processing facilities to retailers involves careful logistical planning, ensuring that consumers receive fresh, high-quality bananas at the right stage of ripeness. In cases where bananas are shipped internationally, advanced tracking systems monitor temperature conditions throughout transit, guaranteeing optimal quality upon arrival. Bananas destined for large-scale retail distribution often undergo one final quality check upon arrival at regional distribution centers. Here, ripening specialists assess the fruit's condition and determine whether ethylene gas exposure is necessary to accelerate the ripening process before shipment to supermarkets. Once the bananas reach grocery stores, they are displayed in carefully arranged sections to attract customers while minimizing handling damage. As the bananas move through the processing facility, their journey continues with additional quality control measures. Every banana that passes through the system is subject to strict oversight to ensure it meets the standards set by global markets. Some bananas are set aside for immediate export, while others are prepared for processing into various banana-based products. Each batch is tracked using barcodes or digital systems to maintain traceability, allowing factories to monitor their origins and ensure compliance with regulatory requirements. Bananas that are destined for further processing must first undergo additional cleaning. Large industrial washers use gentle streams of water combined with food-safe sanitizers to remove any remaining residues from the outer peel. For bananas that will be processed into products requiring peeled fruit, high-efficiency peeling machines are employed. These machines operate with incredible precision, using rotating blades and suction systems to remove the thick banana skin without damaging the soft fruit inside. The peeled bananas are then conveyed along sanitized belts toward the next stage of production. For bananas intended for drying, the peeled fruit is sliced into uniform pieces using high-speed industrial slicers. These slices can be adjusted to produce different thicknesses depending on the desired final texture of the dried product. Once sliced, the banana pieces are spread out evenly on large drying trays or conveyor belts, ready to enter specialized dehydration chambers. The drying process typically involves controlled exposure to warm air, which removes moisture while preserving the fruit's natural sweetness. The temperature and humidity levels are carefully monitored to ensure the bananas do not become too brittle or lose their natural flavor. Depending on the facility, some manufacturers may opt for freeze-drying techniques, which use a vacuum process to extract moisture while retaining the fruit's structure and nutrients. Banana chips, a popular snack food, require a different production approach. Instead of dehydration, the sliced bananas are deep-fried in vegetable oil at high temperatures. Large industrial fryers are used to ensure an even cooking process. The frying time is precisely calibrated to achieve a crisp texture without overcooking or burning the banana slices. Some manufacturers enhance the chips by seasoning them with salt, sugar, or other flavorings before they are packaged. Excess oil is removed using centrifugal draining machines, which spin the banana chips to ensure a light and crispy texture. Banana puree production follows another distinct processing pathway. After peeling, the bananas are mashed in large industrial pulping machines. These machines use rotating blades or rollers to break down the fruit into a smooth, consistent mixture. To prevent oxidation and maintain the puree's natural yellow color, antioxidants such as ascorbic acid are often added during this stage. The banana puree is then subjected to pasteurization, where it is heated to a controlled temperature to kill any harmful microorganisms while preserving its nutritional content. Pasteurization is critical for extending the shelf life of banana puree, making it suitable for use in baby food, smoothies, and baking applications. Once the puree has been properly treated, it is packaged in large industrial containers, aseptic pouches, or smaller retail-friendly jars, ready for distribution. Every stage of banana processing requires stringent hygiene controls. Factories implement rigorous sanitation protocols, ensuring that all equipment, conveyor belts, and processing surfaces are regularly cleaned and sterilized. Workers involved in banana handling follow strict hygiene guidelines, wearing protective gloves, hairnets, and sanitized uniforms to prevent contamination. Automated monitoring systems continuously track environmental conditions, ensuring that temperature, humidity, and air quality remain within optimal ranges. Once processed, bananas and banana-derived products are carefully packed to prevent damage and preserve freshness. For fresh bananas, packing stations use automated sorting machines that place the fruit into protective cartons, ensuring uniform weight and size distribution. Banana chips are packaged using nitrogen-flushed bags to prevent oxidation and maintain crispness. Dried bananas and banana puree are sealed in airtight containers, minimizing exposure to moisture and contaminants. Packaging materials are chosen for their durability, ensuring that products remain intact throughout transportation and storage. After packaging, the bananas are prepared for distribution. Fresh bananas are loaded into climate-controlled shipping containers that maintain a stable temperature between 13 and 15 degrees Celsius, preventing premature ripening. These containers are equipped with ventilation systems that regulate air composition, ensuring optimal freshness upon arrival at their destination. Processed banana products follow a different logistics chain, with dried bananas, chips, and puree being transported in standard freight containers under controlled storage conditions. Ripening facilities play a crucial role in the banana supply chain. Upon arrival at distribution centers, fresh bananas may be placed into specialized ripening rooms, where controlled amounts of ethylene gas are introduced. Ethylene is a natural plant hormone that triggers the ripening process, allowing bananas to develop their characteristic yellow color and sweet flavor. Ripening rooms are carefully monitored, with temperature and humidity levels adjusted to ensure uniform ripening without over-ripening or spoilage. Once the bananas reach the desired ripeness, they are shipped to supermarkets, where they are displayed for consumers. In modern banana factories, automation is increasingly integrated into the production process. Advanced robotic systems handle delicate fruit with precision, minimizing bruising and maximizing efficiency. Optical sensors analyze banana quality, sorting them based on color, size, and ripeness. Conveyor belt systems are equipped with real-time monitoring technology, allowing factory managers to track production rates and detect potential issues before they impact output. The integration of data analytics and machine learning further enhances production efficiency, optimizing banana processing workflows based on demand trends and supply chain logistics. Sustainability is also a growing focus in banana manufacturing. Many factories implement eco-friendly initiatives to reduce waste and energy consumption. Banana peels and rejected fruit are repurposed as organic compost, animal feed, or biofuel. Some facilities incorporate solar panels and energy-efficient machinery to lower their carbon footprint. Water recycling systems help minimize water usage, ensuring that banana processing remains environmentally responsible. Efforts to improve fair trade practices and support banana farmers have also gained traction, ensuring ethical and sustainable sourcing of raw materials. Banana production is a complex and highly coordinated process that involves multiple stages of handling, processing, and distribution. From the moment bananas are harvested on plantations to the point where they reach consumers as fresh fruit or processed products, every step is meticulously managed to maintain quality, safety, and efficiency. Advances in technology continue to refine banana processing methods, making it possible to deliver high-quality bananas and banana-based products to markets worldwide. As the banana industry evolves, manufacturers continue refining their processes to improve efficiency, reduce waste, and maximize product quality. The journey from banana plantations to industrial processing facilities is a highly orchestrated operation involving both traditional agricultural techniques and cutting-edge automation technologies. At every stage, from harvesting to packaging, strict protocols are followed to ensure that only the highest quality bananas make it to market. Once bananas have been harvested and sorted, those destined for industrial processing are transported in specialized containers to prevent damage. The journey from the plantation to the factory is carefully managed, with transportation schedules optimized to reduce delays and prevent premature ripening. Bananas that arrive at the factory in a raw state are first subjected to an additional round of inspections. Quality control teams examine each shipment, ensuring that the fruit meets the necessary criteria before it proceeds to the next stage. Upon arrival at the processing facility, bananas undergo a pre-treatment phase. This begins with a thorough cleaning process, where the fruit is washed in large, food-grade water baths. These washing stations are equipped with high-powered jets that remove any residual dirt, pesticides, or surface contaminants. Some factories add mild disinfectants or organic sanitizing agents to the water to eliminate bacteria and fungi that could affect the final product's shelf life. Once washed, the bananas are conveyed to sorting lines, where automated systems use sensors to categorize them based on size, ripeness, and surface quality. For fresh banana packaging, the bananas that meet industry standards are arranged into clusters and gently placed into protective cartons. Advanced robotic arms are sometimes used to handle the fruit, ensuring minimal human contact and reducing the risk of bruising. Packaging lines use precision weighing systems to guarantee uniformity in product distribution. Some packaging facilities use modified atmosphere packaging, where the oxygen levels inside the packaging are carefully controlled to slow down the ripening process. Bananas that are set aside for further processing move to dedicated peeling stations. Peeling bananas on an industrial scale requires specialized machinery that can efficiently remove the thick outer skin while preserving the soft interior. High-speed mechanical peelers use a combination of cutting blades and suction mechanisms to remove the peel in a single motion. For certain banana-based products, additional peeling techniques are employed, such as steam-assisted peeling, where a rapid blast of steam loosens the peel before mechanical separation. Once peeled, the bananas are inspected again to remove any that are overly bruised or damaged. The peeled bananas are then directed to their respective processing lines based on the final product they will be used for. Bananas designated for puree production are immediately transported to industrial mashing machines, where they are blended into a smooth consistency. These machines operate at high speeds, using rotating blades or pressure systems to break down the fruit into a fine pulp. To maintain the puree's natural color and prevent oxidation, citric acid or ascorbic acid may be added. The puree is then filtered to remove any fibrous material or unwanted solids, ensuring a smooth and consistent texture. Bananas intended for drying are sliced using automated slicing machines that produce even, uniform pieces. These banana slices are then placed onto mesh conveyor belts, which carry them through drying tunnels. The drying process varies depending on the manufacturer, but it typically involves controlled exposure to warm air at temperatures between 50 and 70 degrees Celsius. This gradual dehydration process removes moisture while preserving the natural sugars in the fruit, resulting in a sweet and chewy texture. Some manufacturers opt for freeze drying, which involves rapidly freezing the banana slices before placing them in a vacuum chamber to remove moisture. This method helps retain more of the banana's original flavor and nutritional content. Banana chips, a widely popular snack, undergo a frying process to achieve their crispy texture. The peeled bananas are first cut into thin slices before being submerged in large vats of hot vegetable oil. The frying process takes only a few minutes, during which the banana slices turn golden brown and develop their characteristic crunch. After frying, excess oil is removed using centrifugal draining machines, which spin the chips at high speeds to eliminate any remaining grease. To enhance flavor, the banana chips may be lightly salted, sweetened with honey, or coated in flavored seasonings before being packaged. Throughout every stage of production, factories implement rigorous quality control measures to ensure food safety and consistency. Optical scanners and high-speed cameras are used to detect imperfections, sorting out any defective bananas or banana products. Workers in food safety laboratories conduct regular microbial testing, checking for bacteria, yeast, and mold that could compromise product quality. Metal detectors and X-ray machines scan packaged products for any foreign contaminants before they are cleared for distribution. The final stage of banana processing involves packaging and storage. Fresh bananas are packed in ventilated cartons that provide airflow to regulate ripening. Banana chips and dried banana products are sealed in airtight packaging to maintain freshness and prevent moisture absorption. Banana puree is packaged in sterile, food-grade containers, which are often vacuum sealed or heat treated to ensure an extended shelf life. In large-scale food manufacturing, bulk containers of banana puree may be shipped to other processing facilities, where they are used in products such as baby food, smoothies, yogurt, and baked goods. Once packaged, the banana products are stored in climate-controlled warehouses before being transported to retailers and distribution centers. Logistics teams carefully plan shipping routes to minimize transit time and ensure that the products arrive in optimal condition. Fresh bananas are typically shipped in refrigerated trucks or containers, where the temperature is carefully regulated to prevent premature ripening. Ripening centers at distribution hubs monitor the banana's condition, exposing them to controlled amounts of ethylene gas when necessary to trigger the final ripening process before they reach grocery store shelves. Banana factories continuously innovate to improve efficiency and sustainability. Many facilities have adopted eco-friendly initiatives to reduce waste and energy consumption. For instance, banana peels and other byproducts from the production process are repurposed as compost, livestock feed, or biofuel. Some factories incorporate water recycling systems, filtering and reusing water from the washing process to minimize resource consumption. The use of solar energy and other renewable power sources is also becoming more common in banana processing plants, helping to reduce the industry's overall carbon footprint. The integration of smart technology and automation is revolutionizing banana production. Artificial intelligence, AI, and machine learning algorithms are used to optimize sorting, detect defects, and predict supply chain trends. Advanced robotics are being implemented to handle delicate fruit more efficiently, reducing human labor costs while increasing processing speeds. Data analytics tools allow factory managers to track production in real time, making adjustments to improve efficiency and reduce waste. The demand for banana-based products continues to grow, driven by consumer preferences for healthy, natural snacks and ingredients. Banana processing plants are expanding their product offerings to include innovative items such as banana flour, banana-based protein bars, and freeze-dried banana snacks. The industry is also focusing on sustainable sourcing, ensuring that bananas are grown using environmentally responsible farming practices that support fair wages and ethical labor conditions for workers. As the banana industry expands, factories are continuously developing new techniques to optimize efficiency, reduce waste, and maintain high product quality. The production cycle is carefully monitored, from the moment bananas are harvested in plantations to their transformation into various consumer products. Each stage is executed with precision to meet global market demands while ensuring sustainability and food safety. Once fresh bananas have been sorted, cleaned, and prepared for processing, the next step depends on their intended use. Some bananas will be packaged for fresh consumption, while others will be transformed into banana puree, dried banana products, or banana-based ingredients used in food manufacturing. For fresh bananas, factories implement protective packaging solutions to prevent bruising and ensure that the fruit remains in excellent condition throughout transportation and storage. These packaging solutions may include cushioned cartons, foam inserts, or breathable plastic wraps that regulate moisture levels and slow down ripening. Fresh bananas are often shipped in refrigerated trucks that maintain a stable temperature of around 13 to 15 degrees Celsius. This temperature range is crucial as it prevents premature ripening while keeping the fruit firm and fresh. Advanced logistics tracking systems monitor temperature fluctuations in real time, ensuring that bananas are transported under optimal conditions. If temperatures rise too high during transit, the bananas may ripen too quickly, leading to shorter shelf life and increased waste. The journey of M&M's production begins long before the candies take their familiar shape. It all starts with sourcing the finest raw ingredients, ensuring that only the highest quality materials make their way into the manufacturing process. The primary component of M&M's is chocolate, which requires premium cocoa beans. These beans are cultivated in tropical regions across the globe, primarily in West Africa, South America, and parts of Southeast Asia. The selection of cocoa beans is an extremely meticulous process, as the quality of the beans directly impacts the flavor and texture of the final product. Once the cocoa beans are harvested, they are fermented to develop their rich chocolate flavor. This is a crucial step that involves placing the freshly gathered beans in wooden boxes or spreading them out on banana leaves, where they are covered and left to ferment for several days. During fermentation, the beans undergo chemical changes triggered by naturally occurring bacteria and yeast. This process reduces the beans' natural bitterness and enhances the complexity of their flavor profile. Regular stirring and aeration ensure even fermentation, and expert cocoa farmers monitor the process closely to prevent over-fermentation, which could compromise the beans' quality. After fermentation, the beans are dried under the sun, further intensifying their chocolatey aroma. The drying process can take several days and must be carefully managed to prevent mold growth. The dried beans are then packed into large sacks and shipped to chocolate manufacturers, including those that supply chocolate for M&M's production. Once the cocoa beans arrive at the processing facility, they undergo rigorous quality control checks. Samples are taken from each shipment to assess various characteristics such as bean size, moisture content, and aroma. Any beans that fail to meet the strict standards are discarded or repurposed. The approved beans then move on to the cleaning phase, where they pass through specialized machines equipped with powerful air jets, sieves, and magnets to remove unwanted debris such as dust, stones, and plant matter. The thorough cleaning ensures that only pure cocoa beans proceed to the next stage of the process. With the beans cleaned and sorted, the next step is roasting, a critical phase that brings out the rich, deep flavors of chocolate. The roasting process is highly controlled and varies depending on the desired flavor profile. Beans are placed into large rotating drum roasters, where they are exposed to carefully calibrated heat, typically ranging from 250 to 350 degrees Fahrenheit. The length of roasting time can vary from 30 minutes to over an hour, depending on the type of chocolate being produced. As the beans roast, the heat triggers complex chemical reactions, including Maillard reactions and caramelization, which contribute to the depth and complexity of the chocolate flavor. Roasting is not just about flavor. It also helps loosen the thin outer shell of the cocoa bean, making it easier to separate the nibs, the inner, edible part of the bean, from the husk. Once roasting is complete, the beans are cooled rapidly to halt further cooking. They then move to the winnowing stage, where they are cracked open, and the husks are separated from the nibs using a combination of sieving and airflow. The husks, now removed, are often repurposed for agricultural use or discarded. Now it's time to transform the roasted nibs into a smooth, rich chocolate base. The nibs are passed through heavy-duty grinding machines, where they are ground down into a thick liquid paste known as cocoa mass or cocoa liquor. This grinding process generates heat, causing the natural cocoa butter within the nibs to melt and blend with the cocoa solids. The result is a velvety, rich substance that serves as the foundation for all chocolate products, including the chocolate cores of M&Ms. At this stage, the cocoa mass is still quite bitter and lacks the smoothness associated with high-quality milk chocolate. To refine its texture and taste, it is mixed with additional ingredients, including sugar, milk powder for milk chocolate varieties, and more cocoa butter. The exact proportions are carefully controlled to ensure consistency across every batch. The blended mixture is then sent through refining rollers, which grind the chocolate particles to an incredibly fine texture, reducing them to just a few microns in size. This refining step is crucial for ensuring the signature smoothness of M&M's chocolate. But up next, the chocolate must undergo a crucial process known as conching. Conching is an intensive mixing and aeration process that enhances both the texture and flavor of the chocolate. Large, specialized machines equipped with rotating paddles continuously churn the chocolate mixture for several hours, or even days, depending on the manufacturer's specifications. During conching, heat and friction help to evaporate unwanted volatile acids, mellowing the chocolate's flavor and reducing any residual bitterness. This step also ensures that the chocolate reaches an exceptionally fine and uniform consistency, eliminating any remaining graininess. Once conching is complete, the chocolate must be tempered, a carefully controlled process that ensures the chocolate has a stable crystalline structure. Tempering involves heating the chocolate to a precise temperature, cooling it slightly, and then reheating it to another specific temperature. This controlled cooling and reheating process encourages the formation of stable cocoa butter crystals, which give M&M's chocolate centers their signature snap and glossy finish. If chocolate is not properly tempered, it can develop a dull, chalky appearance and an undesirable, crumbly texture. With the chocolate now perfectly tempered, the next step is forming the small, round chocolate cores that will become the centers of M&Ms. The tempered chocolate is dispensed into specially designed molding equipment that shapes the chocolate into tiny, uniform spheres. These chocolate pieces are rapidly cooled to solidify their structure, ensuring they maintain their perfect shape. Once solidified, the chocolate centers are ready for the next stage of production. But before the chocolate centers can move on to the next phase, they undergo another round of quality control. Sophisticated scanning and sorting machines inspect each individual piece for size, shape, and texture consistency. Any chocolate pieces that do not meet the exact specifications are removed from the production line and either reprocessed or discarded. At this point, the chocolate cores are complete, but they are still missing the signature crunchy sugar shell that makes M&Ms so iconic. To prepare for the coating process, the chocolate pieces are carefully transferred to large rotating drum machines where they will be transformed into the colorful candies known around the world. Now it's time to begin the intricate process of coating the chocolate centers with their signature sugar shell. The process starts with a sugar syrup mixture made from granulated sugar and water, which is heated to an exact temperature to achieve the correct viscosity. The sugar syrup is prepared in carefully monitored mixing tanks to ensure consistency across every batch. Once the sugar syrup is ready, the chocolate cores are placed into large rotating coating pans. These specialized pans are designed to gently tumble the chocolate centers, allowing for even application of the sugar coating. The sugar syrup is added in small increments, gradually building up the shell layer by layer. After each application, the candies are briefly dried using controlled airflow to harden the sugar coating before the next layer is applied. This step is repeated multiple times, as the sugar shell must reach the perfect thickness to provide the signature crunch that M&Ms are known for. Throughout the coating process, precise measurements are taken to ensure each M&M receives an even and consistent sugar shell. The candies are inspected at multiple stages to verify their size, shell thickness, and overall quality. Any irregularly shaped pieces are removed to maintain the brand's strict standards. Now it's time to explore one of the most intricate and carefully controlled stages of the M&M's manufacturing process, the creation of the colorful sugar shell. This step is essential as it gives M&Ms their signature crunch, vibrant appearance, and prevents the chocolate core from melting in consumers' hands. The process of coating the chocolate centers in sugar is not a simple one. It requires multiple layers of application, precise drying techniques, and exacting quality control measures to ensure that each candy turns out perfectly. The process begins with preparing the sugar syrup, which serves as the base for the outer shell. This syrup is made by dissolving high-quality granulated sugar in water and heating it to an exact temperature to achieve the desired consistency. The proportions of sugar and water must be carefully controlled to ensure that the final coating will be thick enough to provide a satisfying crunch while remaining thin enough to allow for a smooth, even color application later in the process. Large industrial mixing tanks continuously stir the solution to maintain uniformity, preventing sugar crystals from forming prematurely, which could create an undesirable, grainy texture in the shell. Once the sugar syrup is prepared, the chocolate centers that have been formed and cooled in the previous step are placed into massive rotating coating pans. These pans, also known as dragee pans, are large, circular drums that spin at a carefully controlled speed, allowing the candies to tumble evenly as the sugar syrup is applied. The process of coating the chocolate centers in sugar is known as panning, and it is a delicate operation requiring expert control over temperature, humidity, and airflow. The first application of sugar syrup is extremely light, providing only a thin base layer that helps the subsequent layers adhere properly. After each addition of syrup, a controlled airflow is introduced to the rotating pan to help dry the layer and prevent the candies from clumping together. The drying step is just as critical as the application itself. If the sugar syrup remains too wet for too long, it can result in an uneven coating or cause pieces to stick together, leading to misshapen M&Ms. This layering process is repeated multiple times, gradually building up the shell to its final thickness. Each new layer of syrup must be carefully measured and evenly distributed across all the candies in the pan to ensure a uniform shell thickness. The factory uses automated sensors to continuously monitor the weight and diameter of the candies, ensuring that each M&M receives the same precise amount of coating. If any inconsistencies are detected, adjustments are made in real time to correct the issue. The drying process also plays a key role in determining the final texture of the shell. Factories use sophisticated drying chambers that regulate temperature and humidity with extreme precision. The drying process must strike a perfect balance. Too much heat too quickly can cause the sugar to crystallize unevenly, leading to a rough texture, while too little heat can leave the shell sticky and prone to damage. Airflow systems within the factory ensure that the drying process occurs gradually and consistently across every batch. The next challenge in the sugar coating stage is ensuring that the candies remain perfectly spherical as the layers build up. If the panning speed is too high or the syrup is applied unevenly, the candies can develop a slightly oblong or irregular shape. To prevent this, highly skilled operators oversee the process, adjusting pan rotation speeds and syrup application rates as needed. The use of vibration sensors and laser scanning technology further helps detect any irregularities in shape, allowing for real-time corrections. Throughout this process, thousands of tiny M&Ms are tumbling together in the massive coating pans, yet they must all maintain a uniform appearance and size. To achieve this, the factory employs a combination of mechanical precision and human oversight, ensuring that every step of the sugar coating process adheres to the highest quality standards. This level of detail and control ensures that every M&M that makes it into a package is identical in texture, thickness, and size. But up next, now that the sugar shells have reached the correct thickness, it's time to introduce the vibrant colors that make M&Ms so instantly recognizable. However, before any color is applied, the candies are still a plain white or light beige color, lacking the bright and varied hues that consumers expect. The process of adding color is just as intricate as the coating process itself, requiring precise dye applications, careful drying, and rigorous quality control checks. The first step in coloring M&Ms is preparing the food-safe dye solutions. Each color, red, yellow, blue, green, orange, and brown, is created using a carefully controlled blend of FDA-approved food colorants mixed with water and a small amount of sugar. The color solutions are stored in separate stainless steel tanks, each dedicated to a single hue, ensuring that no cross-contamination occurs. These solutions must be continuously stirred to maintain an even distribution of the dye particles, preventing any inconsistencies that could lead to color variations in the final product. The M&Ms are then divided into different batches, with each batch destined to receive a specific color. The candies are transferred back into the rotating coating pans where the coloring process begins. Rather than applying the dye all at once, it is carefully sprayed onto the candies in multiple ultra-thin layers, allowing the color to gradually build up. This layering technique prevents the formation of streaks or uneven patches, ensuring a flawless and uniform appearance. The rotation of the pans ensures that every candy receives an even coat of dye, but this process must be monitored closely to prevent oversaturation, which could lead to color bleeding or an overly thick coating. The amount of dye applied is measured with extreme precision, and factory technicians continuously test samples to confirm that the color matches the exact shade required by the brand's strict specifications. If even the slightest variation in hue is detected, adjustments are made immediately to correct the issue before the batch proceeds further. After each layer of color is applied, the candies undergo another round of controlled drying. The drying process at this stage is particularly important because it ensures that the color sets properly without smudging or transferring onto other candies. A carefully balanced combination of warm air and controlled humidity is used to dry the candies gently, preserving the integrity of the color while maintaining the smooth texture of the shell. Once the final layers of color have been applied and the candies have fully dried, the next step is polishing, which gives M&Ms their signature glossy sheen. The polishing process involves adding a small amount of food-grade glaze, such as confectioner's glaze or carnauba wax, to the coating pans. As the pans rotate, the candies rub against each other, naturally buffing their surfaces to create a smooth, reflective finish. This step not only enhances the visual appeal of M&Ms, but also serves a functional purpose. It prevents the candies from sticking together during packaging and transportation. Now that the M&Ms have their final color and shine, they must go through one of the most iconic steps in the entire production process: the printing of the signature M on each piece. But before the candies can be stamped, they must be carefully arranged so that each one is properly oriented for printing. High-speed conveyor belts and automated sorting systems position the candies with their flattest surface facing upward, ensuring a consistent print placement. The printing process itself uses an advanced offset printing technique, which allows for rapid and precise application of the white M logo. A specially formulated food-grade white ink, made primarily from titanium dioxide, is applied to a flexible printing pad, which then transfers the design onto each individual candy. The pressure of the printing pad is carefully calibrated to ensure that the ink adheres without smudging or distorting the logo. But this process is not without its challenges. Each M&M must receive a perfectly centered M that is clear and consistent in size. High-speed cameras monitor the printing process in real time, scanning each candy to detect any misaligned or incomplete prints. If a candy does not meet the strict printing standards, it is automatically removed from the production line. This ensures that every M&M that reaches consumers is perfectly branded with the recognizable M logo. With the printing process complete, the M&Ms now have their final appearance, but they must still undergo rigorous quality control inspections to ensure they meet every specification before packaging. This final inspection phase uses advanced laser scanners, weight sensors, and visual inspection technology to detect any defects, such as size inconsistencies, color variations, or improper printing. Any candies that do not meet the standards are removed and either reprocessed or discarded. Now that the M&Ms have their final color, shine, and the iconic M printed on each piece, it's time to move into the packaging stage. Packaging is one of the most important steps in the entire process because it ensures the candies remain fresh, protected, and properly portioned for consumers. The packaging process must be extremely precise, as millions of M&Ms are produced daily, and each bag must contain the exact amount of product while maintaining the highest quality standards. The first step in the packaging process is sorting and portioning. The freshly finished M&Ms are transported from the production area to the packaging lines using specialized conveyor systems designed to prevent damage to the candies. These conveyor belts move the M&Ms in a controlled manner, preventing excessive friction or sudden impacts that could cause the candies to crack or chip. Before the candies reach the filling machines, they must be properly mixed to ensure an even distribution of colors in each package. To achieve this, large rotating drums mix the M&Ms together, creating a balanced blend of all the different colors. This step is crucial because consumers expect a diverse mix of colors in every bag, and any imbalances could lead to dissatisfaction. Sensors continuously monitor the mixture to ensure that no single color is overrepresented or missing from a batch. Once the M&Ms are thoroughly mixed, they move on to high-speed weighing machines that measure out exact portions. These machines use advanced load cell technology to ensure that each package receives the correct weight of product, whether it's a small single-serving bag or a large bulk container. If the weight of a portion does not fall within the acceptable range, the machine automatically adjusts the portion size or rejects the package, ensuring that every bag contains the precise amount of candy. After portioning, the M&Ms are funneled into packaging machines that fill them into different types of containers. The most common packaging formats include small plastic pouches, resealable bags, large family-size packs, and rigid plastic tubes. Each packaging type requires a different filling technique. For flexible bags, the M&Ms are dropped into pre-formed pouches, which are then sealed using heat and pressure to create an airtight closure. For rigid containers, such as tubes or bulk dispensers, the candies are carefully dispensed in controlled amounts to prevent breakage. One of the most critical aspects of the packaging process is sealing. The packaging must create an airtight barrier that protects the M&Ms from moisture, air, and temperature fluctuations, all of which could compromise their texture and flavor. Heat sealing technology is used for pouches and bags, ensuring a strong, tamper-proof closure. For resealable bags, a zipper-style closure is incorporated into the design, allowing consumers to open and close the package without compromising freshness. Each package is then labeled with important product information, including the expiration date, batch number, and barcode. These labels are applied with high-speed printing systems that ensure clear, legible text. The batch number is particularly important because it allows for traceability in case of any quality control issues. If a problem is detected in a particular batch of M&Ms, manufacturers can quickly identify and recall affected products using this tracking system. Before the packaged M&Ms are sent out for distribution, they must pass through a final quality control checkpoint. This stage involves multiple inspection systems designed to detect any defects or contaminants. X-ray machines scan the sealed packages for any foreign objects, such as metal fragments or plastic particles, ensuring the highest level of food safety. Optical scanners verify that each package contains the correct mix of colors and that there are no visual defects in the candies. Weight checking systems also perform one last verification to ensure that every package falls within the acceptable weight range. If any package is found to be underfilled or overfilled, it is automatically rejected and sent back for reprocessing. This level of precision is essential for maintaining consistency across all M&M's products. Once the M&Ms pass the final quality control checks, they are grouped together and packed into larger cartons for distribution. The individual packages are stacked inside shipping boxes in a way that maximizes space efficiency and prevents movement during transportation. These cartons are then sealed and labeled with shipping information, including the destination, lot number, and handling instructions. Now that the M&Ms are packaged and ready to go, the next step is distribution. The packaged candies are loaded onto pallets and transported to regional distribution centers, where they are sorted based on their final destinations. From these distribution centers, the M&Ms are shipped to retail stores, vending machine suppliers, and online fulfillment centers. The logistics of M&M's distribution are highly optimized to ensure that products reach consumers as quickly and efficiently as possible. Temperature-controlled storage facilities are used to prevent the candies from melting or degrading during transit. This is particularly important in warmer climates, where exposure to high temperatures could cause the chocolate cores to soften and the sugar shells to become sticky. To maintain freshness and ensure a long shelf life, M&Ms are stored in climate-controlled warehouses before reaching store shelves. The shelf life of M&Ms can be up to 12 months, thanks to the airtight packaging and stable sugar shell that protects the chocolate from external factors. Retailers follow strict inventory rotation policies to ensure that the oldest stock is sold first, preventing any expired products from reaching consumers. Once the M&Ms arrive at retail locations, they are displayed in strategically placed sections of stores to maximize visibility and sales. The packaging design plays a key role in attracting consumers with bright colors and clear branding, making M&Ms easily recognizable on store shelves. In addition to traditional retail stores, M&Ms are also sold through vending machines, online retailers, and specialty candy shops. While the journey from raw cocoa beans to finished M&Ms is highly complex, the end result is a candy that is loved by millions of people around the world. The precision, technology, and craftsmanship involved in every step of the manufacturing process ensure that each M&M meets the highest standards of quality and consistency. But the innovation doesn't stop there. M&M's production continues to evolve with advancements in automation, sustainability initiatives, and new product development. For example, Mars, the company behind M&M's, has invested in sustainable cocoa sourcing programs to ensure that the chocolate used in their products is ethically and responsibly sourced. They are also working on reducing the environmental impact of their packaging by exploring recyclable and biodegradable materials. Additionally, new flavors and limited edition M&M's varieties are constantly being developed, requiring modifications to the production process. Whether it's peanut butter-filled M&M's, crispy rice varieties, or seasonal flavors, the core manufacturing process remains the same. But new ingredients and formulations require precise adjustments to maintain the signature M&M's experience. The continuous pursuit of quality and innovation is what has made M&M's one of the most enduring and beloved candies in the world. Every bag, from the smallest single-serving pouch to the largest party-sized container, goes through the same rigorous process to ensure that it meets the expectations of consumers.